the audio on that one.
All right. Welcome to our session on private computing. Our first speaker is Dimitris. Take it away.
Yep. Good morning, everyone. My name is Dimitris, and I'm a cryptography researcher at Million. I'm happy to present my joint work with Pratik Sarkar from Super Oracles and Nektarios Tsoutsos from the University of Delaware. This work is called Plasma, Private Lightweight Aggregate Statistics Against Malicious Adversaries. So today we will focus on the problem of heavy hitters, which is that we want to securely compute the most popular client measurements in a privacy-preserving way. In our setting, we have multiple clients on the left-hand side and two servers on the right-hand side. And we want to somehow aggregate their measurements and compute these heavy hitters. It's safe to assume that when we do a large-scale statistics, some of the clients might start misbehaving. A prominent work that addresses this issue is called Poplar, and Poplar works on the two-server model, and it achieves both correctness and privacy against malicious clients. This means that the malicious client that tries to poison the result will be detected by some MPC checks, and also that the correctness, this way the correctness of the protocol will be preserved, and also the privacy of the honest clients is maintained. One problem with Poplar is that these checks are performed under MPC, so they are relatively expensive. Another issue is that since we're working on the two-server model, if one of the servers is malicious, then they can add some noise to the protocol, and the honest server has no way of actually knowing this. So the result of the protocol will not be correct. As a response to that, we introduce Plasma, and we work in the three-server model. And Plasma solves this issue by introducing the third server, and this way we can assume that one of the servers can behave maliciously, and the honest servers will detect this. Additionally, we still preserve both correctness and privacy against malicious clients, but now instead of doing these expensive MPC checks, we rely on some lightweight symmetric primitives that are called verifiable incremental DPFs. So before we talk about verifiable incremental DPFs, a very brief introduction about DPFs. We mentioned about the client measurements, and we can assume that these are bit strings, and we will encode these measurements as a path along a binary tree where it's everywhere 0, except for a specific path that is ones, and like the direction of this path will essentially encode the client measurement. So going right means 1, then left 0 and 0. So with DPFs, what we can do is that we can actually, the client can create two keys, send the keys to the two servers, and the servers can use the keys and expand them to actually acquire secret shares of the original client measurement. And what is important here is that these keys are significantly smaller than actually secret sharing the whole binary tree. So as you can see, we have everywhere additive shares of 0, except for the blue path, which we have additive shares of 1. In an ideal world where everyone is honest, more clients will come, they will generate their keys, send them to the servers, then the server will expand the key, aggregate the trees locally, and by aggregating the trees, essentially they have secret shares of the aggregations of the client measurements, and at the end of the protocol, they can reconstruct this and compute the final aggregation or heavy hitters in our case. And in this example, we can assume that the heavy hitters are essentially the leaves that are above the threshold. Again, here we have the threshold equal to, but can be whatever. And to interpret this result, assume that we have 9 clients, that everyone had the empty string, then 2 of them, their bit string started with a 0, 7 of them, their bit string started with 1, out of these 7, 4 of them had 0, and so on and so forth. So this was the ideal world scenario. Now, when we have malicious clients, what can actually happen is that in each level of the binary tree, they can actually submit more than 1 non-zero values. And since they send secret shares to the servers do not have an easy way of detecting this. Another attack is that at some specific non-zero values, the client can actually force the value to be significantly higher than 1, the shares of the value. So when you reconstruct, for instance, this thing down here, we get 16 instead of 1, which disproportionately influences the result of the protocol. To defend against these attacks, we have a new primitive called verifiable incremental DPFs that does two tricks. So the first one relies on related work from Eurocrypt 2022. And essentially the idea here is to verify that at each level of the binary tree, we have a one-hot vector. To do this, when the servers evaluate the trees, the binary trees, at a specific level, what they end up with is these two vectors, Y and Z, which are vectors of secret shares. And also they acquire some proofs. The idea here is that if the two proofs are equal, the vectors will be one hot when we reconstruct them. The second property of VIDPF is to verify the paths. This means that we want to check that the non-zero values are along the same path, so they are not spread out in the tree, and they are also a correct value. Like in our measurements, we cared about the non-zero values being ones. So what we do here is first we check that the roots are actually a valid measurement. So if we reconstruct the roots, we don't reveal anything because it's a valid measurement. And this is the empty string. And we check that the evaluation is actually one. Next, we can recursively go down the tree and check that the evaluation at each parent is equal to the sum of the evaluation of the children. And this means that the value that we had in the parent is either left or right. Now you can think that it might be split between the two. However, this in conjunction with the previous property that we care that if it's one hot, actually forces the VIDPF to have the non-zero value either left or right. Okay, going back to our problem. So the double voting, we can take care of it by verifying the one hotness. And for the disproportionate voting, we can do this check between the parents and the children and verify that the value that we have at the root, which was one, is correctly propagated down the tree. Another problem that related work had is that since we were in the two-server model, a malicious server could actually disproportionate, again, influence the protocol by introducing some additive error. And you can see now that each server works over their own shares. So the honest server has no easy way to detect this. So in this work, we essentially add an extra server and we work in the replicated VIDPF setting, meaning that we have like different sessions of VIDPFs between the servers. And this way we can check if everything matches at the end. Moving on to experiments, we conduct experiments over both LAN and WAN. And you can see plasma here with the blue, which is this L prime equals 0 means that we did not have any malicious clients there. Then with a green trend, you can see that we have 10% malicious clients. And this is very close in the runtime with the honest clients. And then the related work is higher, takes more time, essentially, especially if when we go for more, when we consider more clients. And another interesting result here that I skipped due to the interest of time is that we did some optimizations to save up on communication. So you can see that although in the LAN we're already faster, when we go to the WAN, this margin actually increases because our communication is significantly lighter than related work. Lastly, we conducted some monetary experiments in the sense that when we spawn up AWS servers, we care about the uptime of the server and also about the communication. And the communication is the most expensive part. And Plasma was the cheapest amongst the related workers. And this wraps it up.
Okay, we have plenty of time for questions. Do we have any questions?
So on slide 7, you showed those properties that you needed, but for the second property, you need the first. But don't you just need to check that every value is binary? You don't need to check that it's actually one hot? I think that's already sufficient.
So the first check checks at each specific level of the tree. The vector is one hot. The second checks that all the one hot values are across the same path, and also that the value is one. Does this cover you?
Yes, I understand the properties, but I think that if you just check the second one and you replace the first one with a check that it's all values are binary without counting,
Oh, okay. I see,
that
I
would
see.
already be sufficient
Got it, got it.
and more
Um,
efficient, perhaps.
But how can you check that all the values are binary?
I don't know.
Yeah, that's it. That's it.
Thank you for the presentation. I have a question regarding the correctness. You say that in order to handle the malicious server, you add an additional server. Can you elaborate more on how it works?
Yeah, so the idea is that we run a VDPF session. So essentially the client, instead of generating two VIDPF keys that sends to one to one server and the other to the other server, essentially now we do it 3 times, the same thing. It's like replicated secret sharing, if you're familiar. So now the client will generate 6 keys and send pairs to the servers. Of course, like each session will need different randomness. Yeah, we'll say the final results.
Do we have any other questions? Pardon me. Okay. Oh,
sorry. So do you think it can be scalable to be more than 3 servers?
It could be. The issue is that with VDPFs, with DPFs in general, the more servers that you use, it doesn't scale very well. So theoretically, you can do it, but like the performance will suffer.
I think we have time for one more question. Oh.
You have added one additional server. What if that server fails at a point? Like how you do you consider that scenario in your work?
So any of the 3 servers can be malicious. And I skipped this, but the idea here is that you cannot know who is the malicious server, but the owner servers will abort the protocol.
Okay, let's thank our speaker again. And I believe our second speaker is online. All right.
Hi everyone, I am Mazharul Islam, a PhD candidate at University of Wisconsin-Madison. Today I will be presenting our work titled Compact Approximating Complex Activation Functions for Secure Computation. This is a joint work with my advisor Rahul and folks from Visa Research. Cloud-hosted machine learning models can provide valuable services. For example, once trained, these models can be used for remote face authentication, performing early disease discovery from users' healthcare data, so on and so forth. However, to enjoy such services, users have to share their private data with the machine learning model. This can raise serious security concerns. For example, shared private sensitive data can be used by the ML model for training without users' explicit consent. Similarly, they could be stored insecurely and could get leaked, shared with third-party services without users' consent. One way to solve this problem is to use secure inference. In secure inference, we use multi-party computation techniques to protect users' data. Client encrypts their data before sending it to the cloud services, and at the end of the secure inference, client learns only the model output of the inference result, and cloud service learns nothing more than what is revealed by the inference result. For secure inference, we need to compute both linear operation that involves vector multiplication and nonlinear operation that involves computing the activation functions. The performance bottleneck of secure inference is computing the nonlinear activation functions. This is because implicit techniques are not specifically suitable for doing nonlinear arithmetic. As such, majority of the existing work focuses on a simple activation function called ReLU. However, there are other complex activation functions that are heavily used by the machine learning community and have compelling advantage. For example, this complex activation function can result in a model that is more robust, have better accuracy, and converges faster. There are few existing approaches. However, one question still remains how accurate and efficient these approaches are as the number of hidden layers of the machine learning model increases. More specifically, by complex activation functions, I am referring to SELU, GELU, and MISH. These functions are challenging to compute using MPC techniques because they have involved highly nonlinear math operations such as tan h of x, ln x, exponentiation of x, or inverse of x. Another challenge is small error introduced in one layer during computation can accumulate and snowball into a large error that result in a significant accuracy loss of the model. Finally, finding the appropriate parameters that are used during the approximation that is both accurate and efficient is challenging. To address these challenges, we propose Compact. Compact can generate MPC-friendly, accurate, and efficient approximations of complex activation functions. It supports three popular complex activation functions, SELU, GELU, and MISH. It performs well even as the number of hidden layers increases. It is compatible with all existing MPC libraries and does not require retraining or fine-tuning the already trained model. To address these challenges, we introduce several techniques. We start by looking at the second derivative of this complex activation function. One can quickly realize that the region that is beyond -5 and +5, we can easily approximate them using two simple polynomials. Next, by focusing on the region that is close to 0, one can see that the second derivative is not flat, which implies that it's harder for us to approximate those regions accurately. We care about accurately approximating the region close to 0 because input to the activation functions are normalized and majority of the input are going to fall into the region close to 0. Next, in the approximation process, we take into account the model and the data set. This is because one approximation that performs well on a given model and a data set may not generalize well for other model and other data sets. Let's try to incorporate these observations into our approximation process. Say we want to approximate the region between -5 and +5 using m piecewise polynomials. Each of these polynomials can have a degree of at most k. The good thing about such piecewise polynomial-based approximation is that each of these pieces is already MPC friendly. However, it is challenging to have accurate approximation that does not affect the accuracy of the final model significantly using such simple idea, especially when the number of hidden layers increases. To have accurate approximation, we use Chebyshev sequence-based approximation for each of these polynomials. This is because Chebyshev outperforms spline or least square fit-based approaches when the function we are approximating is complex. Next, to have accurate approximation near the region close to 0, we introduced a new way to calculate the error of the approximation function that includes the input density. As a result, the approximation process is incentivized to have accurate approximation near the region close to 0. Next, we use binary search to find the appropriate approximation error threshold. Note, increasing approximation error threshold could affect the model accuracy significantly. By reducing the approximation error threshold, we could have negligible impact on the model accuracy. We find the maximum approximation error threshold using binary search such that the model accuracy is not affected significantly. Lastly, observe that finding the appropriate number of piecewise polynomial m and the degree of each of these polynomial k will be dependent on the model and the data set. Increasing m and k will result in more accurate approximation and presumably will have negligible effect on the model accuracy. However, it might not be the most efficient approximation, resulting in high performance overhead. Decreasing m and k will have the exact opposite effect. We can pose this as a constant optimization problem, as I'm going to describe in the next slide. In this constant optimization problem, we are given the model, the data set, and the negligible accuracy loss we can tolerate for secure inference. Typically, it's in the ranges of 1%. Then we use our initial solution of M0 and K0 to generate an approximation. Once we are done, we can check if the generated approximation have negligible impact on the model accuracy. If it's not the case, then we need to increase the value of M and K to generate more accurate approximation. Once we are happy with that the generated approximation have negligible impact on the model accuracy, we can check if it's computationally efficient or not. If yes, then we are done. Otherwise, we will have to decrease the value of M and K to make it computationally efficient. As you can observe, there is a trade-off between increasing the value of M and K on the model accuracy and computational efficiency. To find the optimized value of M and K, we use a simulated annealing framework. Incorporating the simulating annealing framework to solve this constant optimization problem requires a bit more elaborate scheme, which we have described in detail in our paper, and I would be happy to talk about if you have any questions regarding that. Very briefly, here is one of our experimental results from the paper. We compare compact with other approaches to observe impact on model accuracy and inference time. We take a convolutional neural network and use the Cypher 100 dataset. Here, we draw the model accuracy loss of MPC-friendly approximation using different approaches. We find that two approaches generate approximation that have negligible impact on the model accuracy, NFGen and compact. Other approaches have significant impact on the model accuracy. Then we compare compact and NFGen for computational efficiency, and we find as the number of hidden layer increases, our approach compact generates more computationally efficient approximation. In fact, for a 10-layer CNN model, our approach is about 2.9 times computationally faster than NFGen. In summary, we propose compact, a framework that can generate MPC-friendly approximation of complex activation functions. We leverage normalization to generate density-aware accurate approximation. Compact dynamically searches for optimal parameters, and compact generated approximations are efficient and have negligible impact on the model accuracy as the number of hidden layer increases. Thank you all for listening to the talk. I will be online to answer any question.
So we have the speaker on Zoom. He's not online. All right. Okay. I guess then our next speaker is Hiraku.
I think I have plenty of time. So I'm going to talk about the constant run private decision tree evaluation for by using secret sharing data. This is a joint work with Nan and Katerina from University of St. Gallen and Naman from IIT Delhi and Kazunari from the University of Tokyo, and me from Aarhus University and the University of Copenhagen. Let me start with showing the example of the setting of our work. Users on the left and the service provider is on the right. Let's say this service provider wants to provide, for example, healthcare analysis service. And then as a user, you send your personal information to the server or the service provider. Then you will get your analyzed data, for example, if you're healthy or not. In this setting, you have to send your sensitive information, for example, your DNA data or your biometric. Once such kind of personal data is leaked, it's not only your own problem, but sometimes if the DNA data is leaked, it's also your problem for your family. So you do not want to send such kind of sensitive data in plain text form. Also, the service provider doesn't want to store the sensitive data from the individual. So using multi-party computation, you can somehow solve such kind of problems. I wrote 3 servers in the middle. These are often called computing parties or computing servers. They compute the exact same computation, but using multi-party computation. So in this setting, user encrypt their data and send it to these 3 servers. And then 3 servers somehow compute with using these encrypted messages. And in this setting, the users don't have to send the personal information in plain text form, as well as the service provider doesn't have to store the individual personal data. And the secure computation we consider is a private decision tree evaluation. So most of the work, not most of, some work consider secure comparison, some work consider secure division, so on and so forth. But in this protocol, we use secure comparison and some other protocols and combine together and then do the decision tree evaluation. Okay, before going into the technical part, I'd like to share the comparison table. Previous work, most of them required linear round complexity for the computation of PDT. Most recent work by Tsuchida et al. In 2021 constructed a private decision tree evaluation using secret shared data within the constant run, which is 25 rounds. But we thought this 25 rounds was still large when you're using a network with big delay. So this is the starting point. We want to improve the results. Okay, let's get into the private decision tree evaluation. I have a decision tree evaluation, textbook style of decision tree evaluation here. In our work, decision tree consists of, a decision tree is a full binary tree that consists of, each node has the following information, index of attributes, and conditional flag to choose an operand. So you can choose less than protocol or equal to protocol. And the nodes also store a threshold value. So let me give you a concrete example. So let's think that this service is determine your nationality. So you have an input X. So for example, this is my input. I have features or attributes that describes myself. So my height, my weight, the language I speak, so on and so forth. There are other features you have. So you put the input to the service. So in this slide, I show non-MPC style, so just a plain text form decision tree evaluation. The algorithm starts from the root node. So this root nodes, for example, let's say have a index of attributes 1. Then you think of attribute 1, which is weight. And this root node has a threshold. So you compare with your weight with this threshold. Then if the comparison result is 1, you go down to the right. And if the comparison result is 0, you go down to the left. So on and so forth. You do the same thing to the next layer. You pick the index of attributes here. Then if it's the height, you compare it with the height with some numbers. Then you do the same thing until you reach to the leaf node. And then finally you can get the information that I am Japanese. This was done in the plain text form, so non-secret shared form. But you have to do this in secret shared form. All the information are stored in the secret shared form. So you cannot see the data itself, but it's a secret shared or encrypted. So also the inputs features are also secret shared. So you cannot see my height, weight, and language I speak. So we constructed these 3 sub-protocols to construct a private decision tree evaluation. One is attribute selection, and second one is secure comparison protocol, and the last one, path evaluation. In this talk, I only focus on presenting path evaluation. But attribute selection and secure comparison protocols are also interesting. We use one-hot vector technique, which can be also applied to constructing lookup table protocol. And also secure comparison, we use the function secret sharing for that. We combine a very nice share conversion protocol with a comparison protocol to make everything efficient. Okay, let's go to the path evaluation. Let's play with path evaluation in non-MPC setting. So let's assume that you already computed the secure comparisons. So all the nodes already have the results of the comparisons. So it's a 0, 1. So the algorithm starts from the root node. If it's 0, you go on the left. And if it's 1, you go to the right, and so on and so forth. Then finally you can get to the final leaf node, and then you get final result B3. Because in this slide, please remember we reach to the value B3. I will use it later. All right, so in this non-MPC setting, you didn't even care about other nodes, right? You just see the root node, and then if it's 0, you go to the left, and so on and so forth. You only see the nodes on the path. But in MPC setting, you cannot see anything. All the information is stored in secret shared form. So we used a secure tree shuffle protocol using a secure shuffle protocol that's already well studied. High level idea is like this. You have hidden decision tree or secret shared decision tree. You somehow transform it to visible decision tree. So you randomize the tree and then you reveal it. Now you can see it. Okay, let's see that from the top nodes, you see 1, so you go to the right, and then you see 0, you go to the left, so on and so forth. Finally, you reach to the final result B3, which is exactly the same as before. How we did do that? Let's just highlight, let me just highlight this permutation, preserve the relations between parents node and child nodes. So let me show real quick how we do it. Let's assume that we have this aging tree here in the middle. We can pre-compute this, so we can prepare this before protocol starts. And then this is the left-hand side. This is the original tree I showed. And then you see one here. Then you flip the child nodes, the sub-trees. So child's node with connecting with red edge and blue edge swapped, like this. And also you can see one here, and yeah, one here. Then you swap the yellow edge and green edge swap. Then after that, you add this aging tree to the tree. Then it's the tree is randomized, so you can reveal it, and you can get randomized tree. Then you don't need to care about secret shell form. You just see the plain text decision tree. Okay, this is our result. You can see that if the tree is small, like a depth of 5, depth of 7, it's reasonable. We use 3 servers in the world, in San Francisco, Frankfurt, and Singapore. Then the only, to send a message, it takes like around 160 millisecond or 180 millisecond. So if you use our high-run protocol, it takes 800 millisecond for only a communication. So you can see that if the tree is small, like 7, all the execution time is coming from the communication time. And this is sad, but if we consider a tree depth with 15, it takes more time. But we say in the paper, oh, it's still reasonable. Thank you very much.
Okay, we have time for a few questions.
Thanks for the nice presentation. Are you familiar with the systems or designs, for example, sorting hat or level up? The one came in CCS22, another came in CCS23. They are based on homomorphic encryption techniques. They work with one single untrusted server. And for similar tree depth, for example, tree depth 7, they will probably take less than 100 milliseconds. So how do you differentiate your system from those systems, or what are the advantages of using these systems over that system?
Is it a two-party setting?
It's a one single untrusted server and the client. There are no 2 servers, and that is untrusted.
Okay, so computation is only done in this untrusted server, and then
yes,
it's encrypted in homomorphic encryption.
Yes.
That's a good question. So it's a comparison with the construction in homomorphic encryption and construction in secret sharing form like ours. The good point in construction in secret sharing scheme is you only need to care about communication rounds complexity. So yeah, I know. I'm explaining secret sharing scheme. So we only focus on the reducing the rounds. That's how we do it. Then in homomorphic encryption scheme, I suppose the computation is quite large compared to a secret sharing scheme. And also, you have to use oblivious transfer or some other public key crypto systems. So we consider it quite heavy compared to a secret sharing scheme. Oh, okay, thank you for the pointer. I will check. Thanks for the nice presentation.
Okay, I think we have time for one more question for this speaker, and then apparently our last speaker is now on Zoom, so we could take maybe 1 or 2 questions for them.
Hi.
Hi.
Thanks for the presentation. My question is how you find the position of a particular person in a tree, like what you do to estimate that you have to place this particular person at this place. And another thing is you are using the attributes like height, weight, and maybe there was one more attribute, but there can be some overlapping because there may be so many people in a country with that particular height, that particular weight. So how you distinguish like that? So, yeah.
If height is small and speak Japanese, I'm Japanese now. Is that your question?
It's about the uniqueness of the attributes, how you distinguish between users, because they will be attributes that are overlapping.
Actually, it's out of scope. It's a machine learning problem. So we use the learned model. So this model is already learned. So how you distinguish is learned already. So we didn't touch it. So how to distinguish people or how to distinguish these input features, it's out of scope, but it's already learned, used. So we only use the learned model on secret share. Thank you for the question.
All right, thanks, Faraka. And if we have any questions for the previous speaker, we could take them now about approximating complex activation functions. I think everyone.
The question that I had was about your graphs. If I remember in your comparison system, as the number of hidden layers increases, you had kind of linear growth. And I expect the trend for the other one too, but it seemed like it was kind of displaying some sort of exponential trajectory. Is there any reasoning as to why that was the case?
So the question was why the linear growth for the inference time as the number of hidden layer increases?
Yes, that's right. So yours, like I expect that would be a linear overhead, right? Because essentially more hidden layers means exactly that many more approximations that you're performing. But for your comparator, it seemed to show some sort of an exponential growth there on that graph.
Oh yeah, so there are two, firstly, this is a linear graph, but if you're like, as the number of hidden layer increases, the number of activation functions that needs to be computed also increases by constant. So that's one of the reasons. And second reason is that the number of the parameters that are used during the approximation becomes a bit harder to find when the number of hidden layers are more. So that was the second reason, actually.
All right, thank you.
And it's a bit hard to basically come up with a right answer, because as the number of hidden layer increases, it's become harder for us to explain things more easily, because I can explain things what happens to a three-layer neural network, but as the number of hidden layer increases, we lose that kind of explainability. So that was one of the reasons. We attempted to find out, like, plot the error value as the number of hidden layer increases. How does the error propagate? Approximation error propagate, but it's very hard, like, basically to come up with a solid explanation that could be justified.
Okay, thanks.
of this mix does not know with certainty who is communicating with whom. However, can infer a probability by saying, well, there's two messages in, they're blended together, and then they would go to their corresponding recipient. So it's a half a probability for each of these messages, for example, to be from Alice's message. And this is achieved because there is a memoryless property of the exponential distribution. What the memoryless property says that these output messages are equally likely to be one of these output messages, regardless of the arrival of time. It's a nice property. This is why this type of mixing is being used, for example, in NIM. And it allows us to evaluate the anonymity of such system easily. But what happens when we have different traffic types? So let's say Alice, again, same scenario. Alice wants to send a message to Bob and Mary wants to send a message to Charlie. However, right now they are using two different applications and they have two different expectations when it comes to the delays. So Alice is sending actually an email and she would draw the delay for her email from an exponent distribution with a parameter lambda 1. Let's say it's the average delay is 1 minute. And then Mary wants to send an instant message using Telegram and would draw the delay for her message to be spending inside of this mix from a different exponential distribution that has different average latency, and let's say for 5 seconds. And then these two messages leave to their corresponding. The adversary still does not know with certainty which message is going to whom, but the adversary here might actually have some guessing because maybe the message that first earlier came from an instant message because we know that the average delay is smaller, right? So, and we cannot use, in order to evaluate the anonymity, we cannot use the memoryless property anymore because blending these two traffic together actually disrupt this and we do not know how to evaluate the anonymity. So in this work, basically, we're trying to explore all these different questions. Is actually blending traffic, is it useful in terms of anonymity, or do we actually harm the anonymity? And do other factors, such as the number of layers or the number of mixes per layer, do have an impact when it comes to anonymity? But most importantly, how do we even compute the probability, meaning how do we even evaluate the anonymity that is provided by the mixnet in such scenarios? So I'll just give the intuition of how did we compute the probability. I will start with a very simple case. So we're going to have one mix and we're going to have two types of traffic only. And we're going to assume the classic adversary in mixnet, which is a global adversary who's observing all the input and output. And in this first case, we're going to assume that the adversary actually knows the type of traffic of all the input messages. So what that means when he's observing the network, he actually does know the number of messages from each traffic type that is being inside of the mix, right? Because he's a global adversary, knows the type of input, he sees them, so he can figure it out. So the probability of actually, let's say the adversary is focused on the Alice message, and the probability of an output message being this Alice message or being this target message, of course, will depend on the number of messages from each traffic type, which is given by K, the average latency of each traffic type, and the number of traffic type, which is given by this formula. It looks a bit difficult, but it's actually quite easy to understand. But what becomes really difficult is actually how do we compute the probability of the second output messages, all the next messages that they are leaving. Why is that? Because right now, we don't have this K. We do not know, after that first message that left, the adversary does not know the number of messages from each traffic type inside of the mix. Why is that? Because the adversary does not know with certainty what was the traffic type of the first input message. The adversary simply does not know. So we need to rely on also in inferring the probability of all the possibilities of what could have been this first message. So the first message could have been the target message, Alice message. This is what the adversary is interested in. The first message could have been the same traffic type of Alice message, but it's just not the target message that the adversary is interested in. Or the first message could have been simply the other traffic type. And we need to compute all these probabilities in order to be able to compute the probability of all the next messages being the target message. And then we generalize our method for computing all the probability of the next messages and for when we have a big network, because the probability of these messages after these layers will also depend on the probability of being this target message in the previous layers. And we put all this math and this nice algorithm that I will not explain, but all the derivation and the algorithm are in the paper. So just like few results. So actually, we do show that blending traffic actually is useful, if you trust me on this, and because I'll not go into details. And then actually, when we remember when we said the adversary does know the type of traffic of input messages, but even when the adversary knows the type of traffic of the output messages, we show that actually the anonymity level that we get is similar to as if we allocated to a different mixnet to a different traffic type. So we don't lose anonymity when we are blending traffic. And then we also evaluated the anonymity. What if we have only one message from one traffic type and all the other messages are from the different traffic type? And in this case, we actually, this one single message enjoy a lot of anonymity compared to like zero anonymity if we actually had simply two mixnet for different applications. And then, of course, the delay parameter of one traffic type will influence not only the anonymity for that traffic type, but also it will influence the anonymity that other messages from the other traffic type will have. So yeah, in this paper, we have really great work, and we have very great math that is put in very great algorithm, and we also have empirical evaluation that shows different results and how these parameters interact with each other. And basically, the gist of it, we showed that blending different traffic types, whether it's 2 or 3, actually improves the anonymity that is provided by the mixnet in such scenario. And thank you for your attention.
All right. Looks like we have a question up here already.
So thanks for your talking. It's very interesting. And now I have 2 questions. The first one is about the traffic pattern. Like the adversaries knows like different type of traffic. And my question is like, if there is a malicious server, it knows the traffic pattern of the incoming message. And then we see we have another malicious server that is the last layer of the mixed network. It also knows the traffic pattern of the message. And then, it can just link those 2 messages based on the traffic pattern. And you say like you get a higher anonymity. And I'm thinking how you can get a higher anonymity in this scenario, because they can just link the message based on the traffic pattern. And for example, if we have 10% of message for one certain traffic pattern, and then we just decrease the anonymity set to 10% with the whole messages. And my second question is about like, so in this paper, we assume adversaries knows the delay of each traffic pattern. And my question is, if this kind of delay is unknown, so we just assume the clients add some random delay for each layer of mix, and what will be the result? What will be the anonymity? And can we use some proposed method in this paper to analyze this kind of unknown delay in each layer of mix?
So for this, for the second question, yeah, we do assume it's a public parameter. So I don't, and yeah, if you have like instant message that's being deployed, I mean, that parameter, we don't know the delay itself because it's like a random, we're just going to have like an exponential distribution. The parameter lambda.
So you know the parameter lambda, right?
Yeah.
So like in my work, I just let the clients to use different lambda for each layer of mix. And then can we use your method to analyze this kind of scenario?
But why would you have different lambda for different layers?
I mean, for higher anonymity, because like if the adversaries don't know the distribution of the exponential distribution, and then it will be harder to link to message from the outgoing message and the incoming message. So that's my idea. So I'm thinking, can we use the proposed method in this paper to analyze this kind of scenario?
I mean, I'm a bit confused, but yeah, we can talk about it. But the lambda, the probability derivation will not be different if you just choose different lambda. Like it just you have in the paper you have this long math, and you can just plug any lambda you want. It doesn't depend on the specific lambda that you're doing, and then you can do empirical evaluation and see how that impacts the anonymity. Whether it's like the same.
But like the addresses know the lambda, right?
Yeah, because it's public parameter. We're going to assume it's public parameter.
Yeah, but I mean, if we just let clients to choose some random lambda by themselves, and that makes no to sample the data based on the chosen lambda, and
I have a question how this relates to the inter-arrival time of the traffic. For example, if you have one traffic class with a lambda larger than the average inter-arrival time and one traffic class with a smaller lambda, can you give some intuition about how that works?
Yeah, I mean, so it as every academic say, it depends. But yeah, so actually we thought like, oh, so eventually when one higher than the other, both anonymity will increase for both. Let's say we have two traffic types, one that has like very small, like 1 second, and the other one is 5 seconds, so it's close by, right? So eventually both of these traffic will increase. And then we have like different layers and then different levels of anonymity. Then we tried like 10 seconds, 15, but you reach a level where it's actually, this is the maximum they can benefit, and then the difference, the higher the difference gets, then like you kind of like diminish in return. And then it becomes like actually easier for the adversary to know that these messages are coming from different traffic distribution, and then you decrease the anonymity. You do not decrease it below what if you allow two different mixnet, but it just, there is an optimal level, and it depends on your parameter where you have to choose these parameters carefully. Does it answer your question? So if you have like a really high difference, let's say for one traffic type, it's like 5 seconds and the other one is 1 hour, then eventually that's worse than if you have like 5 seconds to like, let's say, I don't know, depending.
Okay, I think perhaps it is best if this discussion is also continued offline in the interest of keeping our session on time. So let's thank Ines again. And our next speaker is Johannes.
So thank you. My name is Johannes, and I'm going to present our work, DVoS, Deniable Yet Verifiable Vote Updating. As you probably know, electronic voting has become a reality. E-voting systems are used in many countries for political elections, but also in many non-political elections, for example, at research institutes, associations, universities, and many more. The main purpose of an election is to determine the will of the voters on a particular issue. And therefore, it's important to follow and implement certain election principles. The first one is to keep individual votes private. The second one is to create an environment for the voters in which they can cast their votes freely without any influence from outsiders. And third, it is important to ensure that the final election result consists exactly of the votes that have been cast by eligible voters, and that no votes can be stuffed or removed or changed during the voting process. Now, for traditional paper-based elections over the past 100 years or so, we have learned how to implement these basic principles in practice. For electronic or online voting, however, this is more complicated. Essentially, on a very high level, online voting works as follows. So each voter enters their vote into the voting device, which sends the digital ballot to the election authority. The election authority processes the digital ballots and finally announces the election result. Now, there are several challenges here. So the first one is that we as human beings, we cannot directly verify the integrity of the digital ballot process or trail. The second one is that without further means, there are several participants, several machines which could possibly learn how individual voters voted. And third, unlike in on-site voting, paper-based on-site voting, there is no secret voting booth which protects the freedom of choice for voters. So over the past 30 years, there have been much work in the community to design and implement solutions for online voting to address these challenges. One of the most prominent ones is the Helios e-voting system, and it implements the following approach, basically. So each voter encrypts their vote under the public key, whose secret key is shared among some election authorities. And then the voters post their encrypted ballots to some bulletin board. And then in the tallying phase, in this case, we use a verifiable mixnet with 2 mix servers. The ballots are re-randomized and shuffled. And finally, they are decrypted by the trustees who hold the shares of the secret key. And all these election authorities, they provide some zero-knowledge proofs that this process was executed correctly. Now, with this approach, we can achieve the 2 most fundamental properties, namely vote privacy and verifiability of the election result. However, this approach has 3 significant privacy-related limitations. The first one is that any observer, by looking at the bulletin board, can see which voters abstained from voting and which ones participated. So you don't have participation privacy. Second, a possible coercer can just look over the shoulder of a voter and see which vote the voter entered, and the voter has no chance but to obey to the coercer, right? The coercer can directly check how the voter voted. And third, since we use a public key encryption scheme here, vote privacy is conditional, which is because public key crypto always reduces to a computational hardness assumption, which may be guaranteed during or shortly after the time of the election, but not necessarily in the long run. So maybe in 20 or 30 years, we have new algorithms or new, more powerful machines with which you can retrospectively break the privacy of today's elections. Okay, I summarize this here. And in our work, we addressed all these issues and proposed, we designed, formally analyzed and implemented a new voting protocol, which we called DVOS, which provides all these features under minimal trust assumptions and in a practically efficient manner. Hopefully this is not mine. Okay, so in the following, I would like to present to you, describe to you the main idea of DVOS and explain, hopefully convince you on an intuitive level why it achieves the properties that I've just claimed. Okay, the main idea of DVOS is that we essentially keep the tallying phase, the verifiable mixnet of Helios, but we change how the submission phase works. And the main idea here is that we add a new party, which we call the posting trustee. Here we have one posting trustee, but there can also be several posting trustees. And we do not want to trust the posting trustee for the basic properties, namely vote privacy and verifiability, but only for the additional privacy features. And the posting trustee, the role of the posting trustee is to add dummy messages to cover the real ballots that have been sent by the voters. And at the same time, these dummy messages, they do not change the real content of the real ballots. And this is how it works. So in the first, maybe I can even use this one. Let me see. Okay. So here, so we divide the submission phase into intervals. And to start with, for each voter, the posting trustee creates a trivial encryption of 0, which encodes abstention, and posts this to the bulletin board. And then during each interval, the voter can decide whether they want to submit a vote or not. So in this case, voter 1 submits a vote for candidate A and sends it to the posting trustee. And for all other voters who did not vote in that interval, the posting trustee simply re-randomizes the existing ciphertext. And at the end of the interval, the posting trustee updates this public ciphertext vector on the bulletin board. And we do this throughout the whole submission phase. And at the end, what is going to be tallied is the last state of this public ciphertext vector. This is how it works. And let me now explain to you why it achieves participation privacy. And the reason is, so if you have a look, for example, at a voter 3 who did not vote, who abstained from voting, then this choice here is indistinguishable from the choices of the from the ciphertext not indistinguishable from the ciphertext, but the choice is indistinguishable from the plain text of the other two voters who abstained, who in fact voted, because we use an NCPA secure public encryption scheme, which is re-randomizable. And let me now explain how a voter can evade coercion, over-the-shoulder coercion. So assume voter 1 was coerced here at that point to vote for candidate A. And then at a later point, when the cursor is no longer on site, the voter simply submits a vote for her favorite candidate, say B. And then, for the same technical reasons, the cursor cannot, in the end, distinguish whether this ciphertext here is a fresh ciphertext or a re-randomization of this one. Right. Now, I'll come to everlasting privacy, to the third property in a minute. But before that, I would like to explain to you how we protect against the possibly malicious posting trustee. Because here, without further means, the posting trustee could just fake everything, right? And we don't want to do that. And for this purpose, we use a disjunctive zero-knowledge proof, which works as follows. So we have two possible cases. In the first case, okay, so the statement here is that we have like an old ciphertext and a new ciphertext, E prime, and we append this zero-knowledge proof to each of these pairs. And so in the first case of the proof, the ciphertext E prime is simply a re-randomization of the previous ciphertext, which is what the posting trustee can prove. And in the second case, this new ciphertext E prime can be a fresh ciphertext for any valid candidate. But for this purpose, you also need to prove knowledge of the secret signing key, which corresponds to the voter's verification key. Right. And in this way, you can ensure that only the voters themselves can overwrite their own ballots, but not the posting trustee. And the zero-knowledge property guarantees that no observer can distinguish between these two cases. Okay, so we have implemented this generic protocol with the state-of-the-art technique for everlasting privacy, which is called commitment consistent encryption. You can find details in the paper. I don't have the time here. And we also provide a lot of benchmarks for our implementation. So just to give you one number here, we use a standard laptop, off-the-shelf laptop, and we showed that you can create, or posting trustee can create 10,000 cover messages per minute on a single core. And you can further optimize this, for example, by reducing the size of the dummy cover. And we showed with some DP analysis that the deniability level is still very good, even if you halve the size of the cover. Okay, so let me summarize. I hope I somehow convinced you that this achieves the 3 privacy features that I've just claimed. And interesting future work could be to complement our pen and paper proofs with a formal computer-aided verification, to do some usability analysis, and also to think about how we can mitigate the assumption that we make here that there is some coercion-free time window after the voter has been coerced. So if you're interested in any and working on any of these points, just feel free to chat with me. Thank you.
All right, I have a question right here.
Sorry, got 2 questions here. First is, since for digital voting, do you consider to prevent kind of like votes selling attack? Like people can just sell their votes to anyone who's willing to buy their votes.
Zero the votes, and then completely understand. So can you maybe rephrase?
Say I'm the voter, and say you're Donald Trump, and
yes,
you can pay me like $100 to buy my votes, and then I will just vote for you.
Yes. So what you could possibly, if you're cryptographically educated, you could send this vote at the very last minute, in the last interval, and then somehow with your cryptographic engineering knowledge, you extract the randomness that you use to encrypt that vote, and then give it to me as a receipt. So there are some works. So our work does not protect against this. we are concerned more about like physical coercion, not so much this kind of, but there are works like Bilinios RF, for example, which present against this, but then they don't have the other privacy features.
All right, I see. I got another question about your like designated verified proof part. You mean, I guess that you mentioned some indistinguishability here.
Yes.
Yeah, it's observer. What kind of observer is here? Since for designated verified proof, if I'm the approver or I'm the kind of a designated verifier, I can actually distinguish.
Maybe I said designated, but I meant disjunctive.
Okay.
It's a disjunctive zero.
Okay, I know.
Hi, I would just need some more detail about how everlasting privacy is achieved in certain aspects. So, first of all, like the zero knowledge proofs, many zero knowledge proofs have computational hiding property. I don't know, do you use some zero knowledge proof that does statistical or perfect zero knowledge?
Yes.
And the second, so the answer is yes to that.
Yeah, for the zero knowledge proofs, yes.
Okay, and the second one is about participation privacy. Can this property be everlasting if it relies on the fact in the NCPA security of the encryption?
Yeah, okay, so we use a specific public encryption scheme, or it's not exactly a public encryption scheme, but a commitment consistent encryption scheme, which has a special feature, namely that you can create a public key ciphertext, and from that ciphertext, public key ciphertext, you can derive an unconditionally hiding commitment. And instead of publishing these public key ciphertexts on a bulletin board, you only publish the unconditionally hiding commitments on the bulletin board, and only the tellers themselves, they would see the public key ciphertext. So you have unconditional privacy towards anyone who verifies the election, but not towards the tellers themselves. Towards them, it's still conditional. Yeah, conditional.
So this commitment cannot have unconditional integrity, which means that...
That's right.
So you mean verifiability cannot be the same level as Helios, for example?
Helios, it's also soundness of zero knowledge proofs is also based on, it's also conditional.
No, I don't think so. Hiding is conditional. The proofs, Helios has end-to-end verifiability against all malicious.
But the zero knowledge proofs are essentially the same, and as far as I know, they are, it's usually these kinds of proofs, Schnorr-like proofs, their soundness is conditional, and you have unconditional. Or
I'm not sure about this,
okay,
but in any case, verifiability relies on,
yes,
that you have to trust some.
Otherwise,
okay,
we're not in an information theoretic setting.
Thank you.
Okay, so maybe we can take Florentine's question while we just get set up.
Okay.
Yeah, thanks. Just one question about participation privacy. So when you explain in Helios that these schemes has not the ability to hide the fact that someone votes, I was wondering whether this non-privacy property is not actually a security necessity, because in the sense that we also want to be sure that nobody in the elections is not someone that does not exist. And to evaluate this, we need to know whether this people.
So you're talking about the issue of eligibility, verifiability, and this is guaranteed with the help of these verification keys. So this guarantees this, and well, why would you want to have participation privacy? For example, if I know that you are, if you vote, then you vote for Trump or for Biden. No, say if you vote for Biden, and I tell you abstain from voting, because otherwise I know that he is going to vote for Biden. I check that he abstained. So then this is. Results into some bias in the election result. So this is why we also want to have participation privacy.
Okay, so but we cannot.
Okay, maybe I think we're all the time, but let's talk offline again. Okay, thank you.
All right, let's thank Johannes again. And for the last talk in our session, we have a familiar face. Demetrius will speak to us again.
Great, thank you. All right, I'm Dimitris. I'm a cryptography researcher at Million, and this work is a joint work with Daniel Masny, Nitrio, Subbo Sengupta, Prasad Buthavarapu, and Benjamin Case. This work is called Delegated Private Matching for Compute. And to introduce you to the problem of the private matching for compute before we talk about delegation, there exists previous work that tries to do unions, private unions. Essentially, we have two parties, party C on the left-hand side and party P on the right-hand side. And here, excuse me, we want to create a union in a sense that each of the two parties will not be able to learn which of the records have matched on the other party, and they don't learn anything apart from some intersection sizes. This is very useful because we can do many applications with that, starting from ad attribution, where on one party you might have ad impressions, like what clicks you have done, and so on. And on the other party, we might have ad conversions. And joining these enables us to see how ads are performing, and later on we can do personalization in a privacy-preserving way, and so on and so forth. So in this setting of private ID, we can assume that both parties, as they run the matching protocol, they are online, and then they continue being online in order to do the downstream computation that I just mentioned. In that setting, both parties can bring some associated data. For simplicity here, let's assume some dollar amounts. And what can happen is that they can secret share this data and run the computation, which is easy to do when we just care about two parties. But when we have multiple parties, this becomes problematic. One of the reasons is that the first phase is the MPC phase to compute the matching. And it's easy to assume that not many parties are interested in doing this computation, this heavyweight computation of computing the private matching. And also, after you do the matching, then you also have to do another MPC computation to do the application. So this is not easily scalable. As a result, we propose the delegated private ID, and we replace the party on the right-hand side with a delegate server. And the idea here is multiple parties can offload their computation, can offload their data over an encrypted form. And then these parties also have the associated data. And at the end of the protocol, the ideal functionality that we have is that both party C and the delegate party can end up with secret shares of the associated data for the roles that have matched. So if an identifier exists in party 1, let's say, and also in party C, then both parties D and C will end up with secret shares of the associated values for the row that has matched. And for every other row, we will end up with secret shares of 0. We quickly realized that although previous works have focused on joins and on unions and intersections, we actually can do something different here, and we focused on left join. The reason that we focus on left join is that when we have two parties, we have this associated data that both parties can bring in the computation. The associated data can be the dollar amounts that I mentioned, some timestamps, and so on. And again, this highly depends on the application. But now that we're in the delegated setting, and all the parties P send their data, and then they can go offline, then there's actually no reason of keeping the rows that are not present in parties C dataset. So just by focusing on the left join instead of the union, we can essentially speed things up. In the paper, we studied two protocols. Both of them have party C and party D, the delegate server. And the second one also has an additional party, which we call a shuffler. And then the input parties are multiple parties P, which offload their data. In the interest of time, I'll focus on the first one. The second one is also on the paper. So I'm abstracting out a lot of details here. I hope you get the general idea. And on the right-hand side, because many parties will not fit the slide, I just assume one party, but having multiple parties is the same, essentially. So party C has a database of 4 items, and party P has a database of 3 items, and party P also has these associated values, the dollar amounts. First, what both parties do is that they use some secret local key to encrypt their identifiers, and then the party P uses a key encapsulation mechanism to essentially create some symmetric keys and some ciphertexts, and uses the keys to blind the associated data. With that, party P also uses this public key and encrypts the associated data, sends everything to party C, and then party P can go offline. From here, party C applies the red encryption over the green encryption and sends everything to party D. Now party D has everything they need to do in order to continue the computation. They have their blue key, so they can remove the blue layer of encryption. Now party D acquires the green key and can remove the green layer of encryption from the identifiers. And party D can now perform the matching between the different identifiers. One problem here is that since party D performs the matching, they actually learn the intersection sizes between party C and each of the databases of parties P. So for each row that has matched, for instance, Alice here, what party D will do is that it will send over the ciphertext, which they acquired from the key encapsulation mechanism, and party C will decrypt this and acquire the same key. This is the definition of a key essentially. For the rows that have not matched, party D will just create a new encapsulation, keep the local key, send over the ciphertext, and by decrypting, party C will acquire the same key. So essentially, effectively now that both parties have ended up with secret shares of 0 for the rows that have not matched, and secret shares of the associated data, the initial associated data for the rows that matched. So this has a problem, and what I mentioned before, that since party D performs the matching, if we have multiple parties P, D will learn multiple intersection sizes. In some cases, that's okay. In some cases, that might be very problematic. So to solve this problem, we have the second protocol, which I will skip from this presentation. But the high-level idea is that we have a new OPRF that allows multiple senders to send their data. And then we can re-randomize the ciphertext and also shuffle them. And we use this property to essentially mix data from multiple parties P and hide all these intersection sizes when the delegate node performs the intersection or the left join. Moving to experiments, the simplest scenario, we have one party P, and this does not do justice in our work because we focus on the multiple parties P on the right-hand side. But with one party, and this is with increasing database sizes, you can see that our works are somewhere in the middle. Below the blue and the orange, which are the two protocols that we have created, is the private matching for compute, which is a very similar work, but without the associated data. So this work essentially assumes that both parties are online. Since they are online, like the associated data can offload it later on. However, in our protocol, all our communication has to carry this associated data. So this extra overhead comes mostly from communication. And then fastest is the circuit PSI, which is actually really good. However, again, this is only focused on two nodes. When we go to see the runtime of each party P, and here's like where our work is interesting, is when the data set of the parties P is small, then the party is only doing linear work to their data set size, and then they send their data and they go offline, which is not the case for other protocols that require both parties to be online all the time. To wrap up, we have delegated protocols, two new delegated protocols that allows multiple parties to offload their data and perform the matching, and then the delegate server and also the party C can run different applications, different MPC applications based on the secret shared associated values. These applications could include ad attribution, personalization, and so on, any other computation that you can do over secret shared data, essentially. And we solve the problem of the intersection sizes with a new OPRF primitive that does shuffling and randomization. Thank you.
We have time for a question or two.
Yeah, so thanks for the presentation. So if I understand correctly, so you have this, in your process, you have these two layers of encryption, and you assume that you're able to remove the inner layer without touching the outer ones, right? So you do set this condition on your...
Yeah, that's correct. So it's some type of homomorphism that goes on there.
Okay, so you require some homomorphic property.
Yeah, it's just this exponentiation, has an exponentiation. So when you exponentiate both, like you can remove one of the two exponents, so you end up with the other. But you can instantiate it with different schemes as well. In the paper, we try to abstract it out as much as, and for the CAM as well, we have a very similar property. But for the CAM, how we instantiate it versus how we present the protocol, you can do different things there.
Okay, thanks.
Thank you for the nice presentation. My question is more general one. How does it scale with the increasing number of parties?
So we have some graphs on the paper. I just picked two out of them. The good thing, when I go here, for instance, this is just one party, and both parties have the same database size. So now if instead of one party have 10 parties, parties P, each of the parties P essentially does one-tenth of the work, whereas the total execution time remains the same. So it's kind of heavy for party C, but for party C, like the smaller database you have, like the better it is.
Okay, thank you.
Okay, let's thank all our speakers again. And that concludes the session.
are about. Okay, I think it swapped the view for some reason. I don't know why it's swapping the view. It is a mirror. Okay, folks. Perfect. Yeah, sorry. Okay, so we saw what snarks are. So what there are like numerous snarks constructions that you would have come across. So which one do we care about? Today's talk would focus on the specific construction of snarks called Plonk, which has some nice properties. So particularly it has like constant proof size, and the verifier time doesn't depend on the circuit size at all. It only depends on the statement size. So constant verifier time as well. And the prover time, of course, still grows with the circuit size as with any other proof system. But why Plonk beyond, this nice property of constant proof size? There are also other snarks with that. Well, one, it has been widely used in practice. If you think about like the proof size in actual, it'll be a couple of bytes long. And in addition, it has this very nice property that it supports additional custom gates besides your regular AND OR gates. Addition and multiplication. And, also lookup gates, which are very important for several applications that you could think of. So this is why we focus on Plonk. But, beyond just plugging in Plonk for any particular circuit computation, what is the kind of bottleneck that you can think of? For that, let's look at an example scenario of trying to build snarks for this very specific computation, which is executing nested ifs. Okay, so it's as it says, it's very clear. This is the tree of all possible things, and the alphabets you can think of like code snippets or a circuit representation of a specific segment. And, it's a nested if, which means, let's say the green highlighted portion is what gets executed and continues to do so. And if you see only part of the circuit is executed, whereas the entire circuit is much larger. And so specifically, if the height is L, one drawback of directly plugging in an existing snark or something like Plonk is that your prover compute time typically will grow with 2 power L, which is the size of the whole big circuit. So this is not something you want to do. It's very wasteful because the active circuit is only, of the size L path, which is L by 2 power L is what is active. So you don't want to pay this price. And that's going to be the focus of where we are targeting the problem at. So we need to extend, first of all, this model of compute to beyond nested ifs. That's one example I took. And this is what we first defined in our model, which we call layered branching circuits. So what you can think of this model as is there are n possible, at each step, there are n possible codes or circuits that can be picked out of. And one amongst them gets executed in every step. So there's one that's picked out of these n, and all of these circuits are of the same size S. Okay, so the orange blocks here indicate selecting the relevant code segment during your active phase of execution. And this you end up executing for k steps, let's say. Okay, so the total circuit size here is n times k times S, because every circuit is of size S. And you essentially have the same choice of n segments for each step. Okay. Okay. Yeah, so this is how you would view it in the active phase, right? So all the green segments is what gets triggered in the active phase. 1 out of n gets executed at each step. And, you can even ignore the orange blocks and think of them as being somewhat hardwired in this linking that I've done. Like the active circuit itself, the execution itself takes care of the next input that gets triggered and so on. Like you can think of the encoding as taking care of that. So if you see the active size is of circuit is of size only k times S. And this is where we want to, the prover size ideally should only depend on this.
So if you see this model, apart from nested ifs, which is what I showed you, it also captures this very important application of roll-ups in blockchain. So you can think of n, the number of possible choice of codes, to be like the possible transactions to be executed, and at each step, one amongst them, gets executed. So you can think of roll-ups as getting satisfied by this application, by this model as well, which is why this particular model is what we focus on. And the question we ask is, can we build snarks for layered branching circuits where the online prover time only grows with the size of the active circuit, which is k times s? So this is what I promised. And of course, we will allow the prover to do one-time, input independent pre-processing, which of course has to depend on the entire circuit. This would be true. But given that in the online phase, you only want to pay price proportional to k times s. So that's what we ask. And of course, we are not the first people to ask this question. There have been several lines of works that consider different models, different scenarios. In the interest of time, what I can tell you is there are these 4 sort of broad technical areas that have been addressing this problem. So one is like a la carte proof cost. There are a couple of works doing that. Then there is non-uniform IVCs, which also somewhat try to do similar kind of a thing. And then there are Starks and commit and proof snarks, which also have similar kind of ideas of stitching together, these proofs of different active circuits that are being executed. So I won't get into the details. You can look at the paper for comparison or any of these works. But what I can tell you in highlight, right, is if you look at the works highlighted in red here, they all have the disadvantage that the proof size is non-constant, which if you recall from the Planck is what we picked because we care about having constant proof size. If you look at the work that is highlighted in green, which is Mirage, this is something that has input-dependent prover pre-processing, which is not ideal because if you have input-dependent, you cannot use it for multiple proof computation. So this is something we don't want to deal with, and it's not advantageous. And then the works that are in the blue make non-black box use of cryptography. So by which I mean here that they need to prove statements of the form that certain hash computation was done correctly, which means that you can only use snark-friendly hash, which do exist in practice, but ideally you want to build a scheme that essentially does not have statements of that form. So we want essentially, get rid of all these disadvantages. What we have at the end is, we achieve this online prover time that is only dependent on the active size and logarithmically dependent on the number of possible code chunks. And we do this while achieving all the nice properties from what I listed in the previous, as drawbacks in previous works, which is we have black box in crypto, we have input independent pre-processing, and we have a constant proof size. So this is what we achieve in this work. And we carry on all the nice features that Planck has, which means we have universal setup, and we also have support for custom and lookup gates, which means you can plug in, your favorite gates in your circuit that you can think of. Okay, so the main idea, which I won't get into, is that we use something called an extension of lookup arguments, and we extend it to something called segment lookup, which helps you do this. And I would urge you to look at paper, or you can come talk to me anytime, and I would be happy to talk more about it. What I want to mention here is there is a concurrent work that came out around the same time as ours, which uses similar ideas and has online prover cost of O tilde KS. And their work is for the setting where K is greater than N. So there is a dependence on KS alone. And they call it tuple lookup, what we call segment lookup here. In terms of, we also have some experimental results which compare with baseline Planck. So if you just think of Planck as the underlying protocol, here we are stitching together multiple Plancks, so how much price you will pay. And this is the proof size and verification cost. Again, details, I urge you to look at the paper. But we have not, in our code, did not optimize for the reducing the number of pairings. And in fact, there is a follow-up work of ours, which recently came out, and they not only optimize the number of pairings, but they have some new tricks and extend it to something called matrix lookup, which helps you add ZK. And in addition, also improves efficiency of the prover time on top of our work. So that's all I had to tell you. And if you have any questions, I'd be happy to take. Thank you.
Thank you very much, Sruthi. Are there any questions?
Thanks, nice talk. So how much are you assuming about like the different branches, I guess, across time periods? Because on the screen you wrote it as like the same C1 through CN, but can they be different?
So the C1 through CN, each of them is different, but for every step, they have to be the same, like same set of N instructions.
I see.
Yeah, that's also how the applications use it. It's like fixed set of instructions that you have, and then at each step, one amongst these instructions get executed. That's how, for instance, roll-ups work. So you don't have like different set of N instructions.
Okay, cool, thanks.
Hey, thanks for the talk. You mentioned that S has to be the same between the sub-circuits. So what if we have a sub-circuit that does not add up to S? Do we just add like no op instructions?
Yeah, right now, like you'll have to pad or ensure that, it's of same size. That's just like because you need to set those parameters for using the correct setup of long. But yeah, right now, that's the way you do.
Makes sense. Thanks.
Hey, thanks for the talk. I just wanted to ask, and maybe this is my unfamiliarity with the work on snarks, but is the type of problem that this proof is able to prove statements about for the circuit sat language, or like can you prove statements about like other types of languages?
So it could be like anything that can be encoded as arithmetic circuits at the end of the day. So yeah, you can think of.
I see. So the proof statements, can they, like, are they of the form like this is a set of inputs that like makes the output be one?
Yes.
I see. Okay. Thank you.
Okay, thank you. Okay, last question.
Thank you. Great work. And yeah, I'm quite interested in like, it's like a sublinear prover in snarks only works for this specific like nested ifs, where you can just generalize to it. Like
you can generalize. So the
more
model
universal way.
Yeah, the model I displayed generalizes nested ifs is what example I took. You can think of it like a DAG. It could be any, can generalize the computation to anything. So it is, the model captures beyond nested ifs.
So what you are saying is like we can actually like have sublinear prover in doing generating like a snark proofs.
Yes.
Okay.
Thank you.
Thank you. Can we take the first presentation in order? Okay. This second one. Okay. Thanks.
Share this.
Our second presentation is the remote by Xuan Yan for a paper entitled On the Quality of Privacy Policy Documents of Virtual Personal Assistant Applications. Please welcome Xuan, and you can go ahead with your presentation.
Hello, can you hear me? Hi.
Share your Xuan?
Okay.
Do you hear us?
Yeah, I can hear you.
Okay.
So can you like can you see this screen?
Yes,
Like the
yes, we see.
Okay.
Go ahead, please.
Okay. Hi everyone, I'm Fuman Xie from the University of Queensland. And I'm the second author of this paper, and I'm glad to introduce our work on the quality of privacy policy documents of VPA applications. So to explain our work, the first context I want to share is that what is virtual personal assistance? So virtual personal assistant is a AI-based software assistant that can provide the voice-based services. One of the famous examples is Amazon Alexa. With the booming of IoT, VPA become more and more popular in recent years. They can handle a wide range of user requests, like making phone calls, playing music, or controlling smart home devices. Alexa has the broadest third-party integration through the apps, which they call skills. This also means that Alexa may have more problems with the privacy breaches brought by the third-party developers. In fact, studies and reports have already revealed that Amazon Alexa has a risk of data exposure on user privacy. For example, the FTC found that Amazon have allowed unauthorized access to user data and failed to secure users' privacy videos and other sensitive information, leading to the both internal misuse and the potential external security breaches. In response to these violations of user privacy, various countries has also begun to formulate the relevant data protection regulation to safeguard the user privacy. The two most important privacy regulations are the GDPR, established by Europe, and the CDPA in the United States. But however, Amazon Alexa has also get fined more than 800 million for violating GDPR in 2021. And application stores have begun to take actions to comply with the data protection regulations, such as providing the privacy data processing documents like privacy policies. Privacy policy is a statement provided by the app developers. It explains how the apps collect, use, and share users' personal data. It should also tell specific details depending on the app's target user, such as how it protects children's data, how it handles user data in the specific regions. However, what's the current state of the privacy policy in Alexa skills? And in here we have displayed 4 types of examples. And as you can see, the current state of VPA privacy policies can be poor quality and also raise concerns. So in this work, we mainly focus on the 2 research questions. What are the common problems of VPA apps privacy policy documents, and how to guide the VPA apps developers to develop a high-quality privacy policies? To address these questions, we developed a framework named Cooper to assess the quality of the privacy policies using machine learning and NLP techniques. Cooper developed 4 high-level metrics to assess the privacy policy qualities, including the compliance of disclosure, timeliness, availability, and readability. And I will introduce them one by one. For the first matrix, the compliance of disclosure, we totally summarize 11 components that a privacy policy should be included, such as a collection, retention, and the children. We summarize them from the data regulations and some other prior literature. We have proposed a 2-step document processing approach using the NLP and machine learning techniques. As in this example, we have observed that the privacy policies often follow a structured format where their contents is divided into multiple sections, and each introduced by a subtitle that summarizes the main contents in the section. So we are starting extraction these subtitles from the privacy policies, and then utilize our trained section title classifier to obtain the section included in the privacy policy and the contents which each section. Like in this example, the information we collect section is categorized under the collect section because the section mainly explains what information the apps collects from the user. And the children information is characterized under the kids section because the section will mainly talk about how the children's data is handled. And after checking this component, we have found that like 19% of the privacy policies of the skills have missed covering at least one component. And next, we will move to the timeless quality matrix. According to the CCPA, it says that the developer must update their privacy policy at least every 12 months to keep it current. And in order to check this, we have used the Wayback Machine, which help us to find the 3 timeless data from the privacy policy web page, which are the first time of the privacy policy release, the last time of the privacy policy update, and the uniqueness of the web page. And for this check-in, we found that the more than 800 of privacy policies, which is more than 16% of privacy policy, are never updated in Alexa skill store. And we have also found that the release of the privacy policy does not comply with the release of its skills. And the next finding of our paper is that the number of the privacy policies updates usually increase right after the occurrence of the security incidents. Like in this example, in 2020, Alexa has get a big fight by the privacy regulation. So the privacy policies start to update frequently. And the next one is the availability session. For the availability matrix, we conduct 2 check-in. The first one is the link validity check-in. And the second one is the supported language check-in. For the link validity, we have found that the 14% of external links extracted from the Alexa skills privacy policies are invalid. And for the supported language check-in, we've observed that the 14% of skills do not provide the required language version of their privacy policy, just as they're declared in their skills. And the last one is the readability matrix. And in readability matrix, we have conduct 5 tests. The first test is a double negative. We conduct this test because the privacy policy should avoid double negative sentences to avoid the ambiguous or misunderstanding. And the next one is the obscure language qualifiers, because privacy policy should be avoided as much as possible to use the ambiguous word like the may or possible. And the next one is the main idea as a beginning. So developers should put their main idea as the beginning of the sentence, so it will be more easy for user to understand. And the fourth one is the text structure. We have used the 3 readability matrix and the 7 document structure matrix to measure the privacy policy's readability. That include like the readability index or the ease score. And the last one is a logic order. Some literature have summarized the 4 privacy documentation logic orders. For example, in a privacy policies, developers should first declare the collection, their collect data information first, and then say how to use the collection data, and then how to share the data. We have listed orders and the actual order in Alexa skills in this PowerPoint. And after this readability checking, we got 2 main findings. The first one is the most sentences in privacy policies do not conform to users' reading habits. And the next finding is that the organization of the section order generally meets the user's expectation, while the children and region are expected by the user to appear earlier in data use, and the data use can appear later. And the next is our discussion section. So how can Cooper inspire current privacy policy ecosystems? So we give our discussion from 2 sides. The first side is from the store operators. We recommend the operator should include a quality checking in the app vetting process, and to ensure the privacy policy fulfill the 4 quality metrics before accepting their updated apps. And for the app developer sides, the privacy policy should cover every stage of the processing personal data of data subjects. The privacy policy should also be keep updating. And they should also place emphasis on the implementation of the localization strategies and practices. And the last, the privacy policy should provide the information in the logic order. And thank you. That's all for this presentation.
Thank you very much. Are there any questions for the presenter?
Hi, thank you for your very interesting work. I'm not that familiar with the ecosystem, so are the privacy policies extracted directly from some Amazon repository or something like that? Or did you have to find the privacy policy somewhere, maybe by trying to search the specific service or application somewhere on Google?
Oh, yeah, thank you for this question. For the collection of privacy policy, we just follow a previous works that have a Alexa skills dataset. And for each Alexa skill, it will contain a privacy policy link. So we just using the web crawler to download the privacy policy from that link.
Any further questions? Okay, thank you for your presentation. Thank you very much. Shall we move to the first presentation now? Okay, so we'll go to the first presentation for a paper entitled Flash Swift, a configurable and more efficient range proof with transparent setup by Nan Wang. Please welcome Nan, and you can...
Hello, my name is Nan Wang. Currently, I'm a postdoc research fellow in Cesaro's Data 61. In this video, I'm going to present our work, Flash Swift, a configurable and more efficient range proof with transparent setup. This work is conducted by me and Dongxi. First of all, let me give an outline of our contributions. In this paper, we developed a new logarithmic-sized zero-knowledge range proof called Flash Swift in the discrete logarithm setting without using a trusted setup. It can prove that a committed value lies in the range between 0 and 2 power n minus 1. We integrate the techniques of the two state-of-the-art D-log-based zero-knowledge range proofs, namely Flash proofs and Swift range. To the best of our knowledge, it is the first configurable range proof that is adaptable to various scenarios with different specifications. The configurability allows to trade off communication efficiency or computational efficiency. At the time of writing, it also creates two new records of the smallest range proofs, 289 bytes and 417 bytes for 8-bit and 16-bit ranges among all the bit decomposition-based ones without requiring trusted setups, respectively. It is well known that zero-knowledge range proofs involve large amounts of communication and computational costs, significantly impacts the performance of associated applications. The performance of the incumbent bit decomposition-based zero-knowledge range proofs remains suboptimal, constraining the broader usability and adoption. Moreover, a new problem is generally neglected for those resource-constrained devices. In case of any changes in efficiency requirements, software upgrades of a different range proof can be both energy and time-consuming. So we wonder, curiously, is there a way to combine the strength of the state-of-the-art range proofs to produce a stronger and a configurable alternative without resorting to a trusted setup? Let us have a quick look at the features of Flash proofs and Swift range. Flash proofs and Swift range are two variants of the bit decomposition-based range proofs. Flash proofs is the 3-round zero-knowledge range protocol. It has n power 2/3 sublinear efficiency in both communication and verification. It achieves comparable verification efficiency to that of the most efficient ZK-SNARK that relies on a trusted setup. Swift range is a logarithmic-sized proof with linear verify efficiency. The salient feature is that it achieves twice the verifier efficiency of the state-of-the-art bullet proofs. Our range proof is constructed from public coin protocols. Let me firstly give a simple example on how to construct such a zero-knowledge proof. A zero-knowledge proof is an interactive protocol between a prover and a verifier. It can prove the knowledge of a secret without revealing it. A prover sends an initial commitment. Then the verifier replies with a random challenge. The prover must send back some values computed with this challenge. And finally, the verifier can use these values to conduct a verification. The popular Fiat-Shamir transformation can help transform the interactive protocol to a non-interactive one. Swift range is composed of a zero-knowledge range protocol, Pi SRG, and a series of compression protocols, Pi QC. The compression protocol can reduce the linear-sized range protocol to logarithmic size. Our high-level idea of integration is to try to replace Swift range protocol Pi SRG with flash-proofs range protocol Pi FRG. However, it is not trivial to combine them together because there is an inherent incompatibility barrier between the two proofs techniques. In the following, we'll give an overview of the techniques of flash proofs and Swift range. Let me begin with an overview of Swift range compression technique. Given a witness vector Z and two generator vectors H and G, satisfying the relation H to the power of Z times G to the power of minus square Z is equal to a group element U. The prover recursively reduces the dimension of generators H and G and the witness vector Z until the dimension is equal to 8. The right subgenerators are raised to the power of C-1 and C-2, respectively. In each recursion, U does not have any exponents. The recursions terminate until the proof size achieved minimum. Let me introduce flash proof's bit decomposition technique. The high-level idea is that if we can show that a value can be represented as a binary form, then we can prove that the value is non-negative. Assume we have a target value small x. It can be represented as the sum of a series values wi. If we can prove that each wi is either 0 or the ith power of 2, then we can say that x is non-negative. The prover firstly arranges the values w in a L times k metric. So she creates a series values VL, where each VL hides k number of w values, separated by k distinct random challenges EK created by the verifier. RL are random values created by the prover. The verifier can create a series values FL by subtracting VL from the powers of 2. Here are flash proof's 3 verification equations. In the first equation, multiplying FL and VL can generate a series cross terms in the challenges EK. If the quadratic terms EK squares are all cancelled out, then the verifier can be convinced that W values are either 0 or some powers of 2. The second equation checks each SK hide the number of W values in the kth column. The third equation verifies that the target value X is the sum of all the SKs. So it means that X is the sum of all the W values in the matrix. The major technical challenge for integration is that only the first equation is compressible. The second and third equations are not compressible. Although there's a witness vector VL in the second equation, there is only one generator G. To make compression possible, there must be a set of distinct generators for all VL values. Clearly, the third equation is not compressible either. So If we only compress the witness vector VL in the first equation, this will lead to the invalidity of the other two equations. So we come up with a solution to address this technical challenge. We leverage the folklore observation that checking two equations g power alpha equals 1 and g power beta equals 1 amounts to checking an equation g power alpha times y plus beta equals 1 for an arbitrary y. We concatenate the first equation and the second one by separating them with a random value y. We then subtly convert the left-hand side of the concatenated equation to the compression-friendly form required by Swift-Range's compression protocol. Next, we try to address the integration issue of the third verification equation. We can combine the right-hand side of the second and third equations by replacing the term sk-1 with the product of x and the remaining terms from S0 to sk-2. Our range proof has a distinguishing feature, configurability from other proofs. With different parameter k, our proof achieves different performance. We have a two-gear setting in terms of computational efficiency. Below gear 1, when k equals 2, our proof had the smallest size but lower computational efficiency. When k equals n power 1/3, our proof had the highest computational efficiency but larger proof size. This property allows our proof to flexibly adapt to changing requirements in performance, eliminating the need for different proof, especially for resource-constrained devices. Rather than performing an upgrade of a new range proof implementation, only a simple parameter k is needed in case of efficiency requirement change. Finally, let us have a quick look at the efficiency comparison with the state-of-the-art range proofs in terms of proof size, prover time, and verifier time. We add a new medium gear setting that demonstrates intermediate performance between the low gear and high gear ones. And we build 4 reader charts for different ranges where the closer the vertices to the center, the higher efficiency. Holistically, we can clearly see that our proofs in the 3 settings are positioned at the innermost part of the reader charts compared to the others. And thanks for watching. Please refer to our paper for more details.
Is none available for questions? Okay. Are there any questions?
Sorry, when you say this is kind of configurable range proof, you mentioned a parameter k. What is k here?
Actually, when we said in flash proofs, all the W values can be arranged in the L times K matrix. So K is the number of columns.
Okay.
So we can change different Ks to achieve different performances of the range proof.
Any other questions? So, none, excuse me, this is not my first, not my area of research, but I'm interested in knowing what's the impact of this work on current real-life applications.
Okay. We have enumerated a lot of privacy-preserving applications in our paper. The most typical one should be confidential transactions on blockchain systems. And another one is like a privacy-preserving data aggregation. So one user submitted their inputs. So to defend against the malicious users are required to provide a zero-knowledge proof to prove their inputs are non-negative, because a lot of inputs in our real-life scenarios are non-negative. Yeah. And there are also like privacy-preserving payment systems. Yeah. Please refer to our paper. Yeah, we have a lot of discussion on that.
Okay. Interesting. Thank you very much. Let's welcome the next speaker for the fourth paper. So is this investigating the effect of misalignment on membership privacy in the white box setting? Please welcome. Please welcome Evis and please.
So basically, I'm presenting this work on behalf
of sure. Which is a very good reason for not being here. So I'll do my best to do justice to the paper and at least give you a sense of what we've been working on. Because this is a very mixed session. Who knows about why, basically membership inference attacks and machine learning models. Okay, so half the room, something like this. Okay, who has already attempted some membership inference attacks on machine learning models? Okay. Okay, good, perfect. Just so that I get a sense of what I should spend a bit more time and a bit less time on. Oops, okay, I'm setting the counter. Perfect. That's my usual disclaimer. So basically, the story goes that machine learning models can, and one could argue actually often, are trained on sensitive data sets. And if the model were to leak information in some ways or forms about their training records, right, that might break users' expectations of privacy. And that might potentially, from a legal perspective, means that machine learning models suddenly become personal data. And there's been quite a large range of work and literature in this field, for those of you who don't know the field, in terms of what can be extracted basically from a trained machine learning models, ranging from membership inference attack. We're going to spend more time talking about this today, but also attribute inference attack. So, if I know part of your record, can I figure out the rest? Property inference attack, so can I extract information about, general information about the data set that was used to train a model. Recent work in correlation inference attacks, so basically does the model somehow remember, correlations between the input attributes of, a classifier, for example, et cetera, et cetera. Membership inference attack are basically, the essence is from the trained machine learning model, can I infer whether a specific record was or was not part of the training set of a model? Why do we care? I think mostly two things. First, in some cases, that is a risk in itself, right? So machine learning model can often be trained, especially when you look at specific classes, on data set where membership, right, being in the data set is in itself a sensitive information. Right, and we've already had, when it comes, for example, to location data, to high-profile examples of, cases where membership was, a true concerns. For example, COVID vaccination. We had an example in location data of a priest, basically, that was found and re-identified allegedly in a data set coming from Grindr, et cetera, et cetera. But we also care about membership because this is kind of the strongest attack, right? The idea is that differential privacy protects against membership, and if you protect membership, then, under certain theories of privacy, you protect against everything else. So that's why there is such a big emphasis, in a sense, on membership inference attack from an empirical perspective, an empirical privacy perspective in the field. So how would an MIA work? So basically, the idea is just, given a record, right, can I, with reasonable confidence, infer whether this record was part of the training set or not? And often how they instantiate it is basically, can I train a model? Can I train, for example, a meta-classifier to distinguish between a record that was seen and not seen during training? The issue is that in practice, right, you're very unlikely as an attacker to have this really clean data set of all of these people have not been seen, all of these people have seen, and this is my model, and just nicely train your meta classifier on these, and then if I give you yet another one that comes from the same distribution, then you will be able to make some inference. And so what people do in practice is they simulate the behavior of the model in a controlled setup using something called shadow models. So what shadow models are basically is you have the attacker data set, a data set that basically you have that looks like the original data set, and you take this data set and you draw from this data set to train what we call shadow models. And basically what you do is that you look at, for every one of those shadow models, how the model behaves when it has seen the record during training, when it has not seen the record during training. So basically, you're artificially building models that look like your target model, but for which you can cleanly control what has been seen and what has not been seen during training, right? And that's basically how you learn and how you train a membership classifier, that then you can, apply this membership classifier to the output of your target model with a target record and come up with a probability. Does that, before I go there, does that make sense? Especially for those who do not know membership? Yeah, good? Okay, perfect. In particular, one area of interest for us has been on-device models, right? So there's increasingly a trend, especially in the AI, LLM, computer vision, to move models to the edge, to move models on your device. That reduces latency, that potentially allows you to keep things more private, or at least that's the theory. And we've seen a lot of models from image model for CSAM detection to large language model moving on device. However, from a privacy perspective, that also changes things, right? It basically means that now that it's on device, right? First, you can you as the model developer lose control over what I use the model for and how many queries I can send, and often also means that I can recover the actual parameters of the model, right? Meaning that the model is not a black box to me anymore. The model to me is a white box, right? As I can, once it's on my phone, I don't know, when Apple came up with their CSAM proposal, right, to basically check images using perceptual hashing on device, I think it took people a few days to basically extract the algorithm and be like, hi, so this is the super secret algorithm that they use to try to check if an image is illegal. And so in theory, at least, right, the intuition is that white box should be attacks with white box should be better than attacks with black box, right? You know strictly more. Right, you can run everything you run in black box, but on top of this, you have the exact architecture, the model weights, and you can compute everything. Right, so from an information theoretic standpoint, you get just a lot more information, and you would expect this to help attacks a lot. Right, I should be able to do so much more with white box access. And so typically, right, one thing that people could do is in the white box setting is basically instead of using just the label, right, you could use the output of the model's internal layer as an input to your meta classifier, right? So you take more information slightly earlier in the pipeline, and you would expect this, in theory, to give you more information, better classification, stronger attack. Which from a privacy perspective also means that if there's any chance that your model is going to be on device, right, what you should protect against from a privacy perspective should be different. However, surprisingly, so far, white box attacks, and there's a range of them, often perform poorly, sometimes worse than black box attack. And when you combine them, and even when you combine them, you usually don't get something that is much better than black box, which is weird, right? It's like literally you have so much more information. You have the exact architecture, the exact weight. You can simulate everything you want. And yet in so many cases, white box does not perform better than black box. There have been a few work who, like, have identified this and basically have developed, workarounds, right? So either you remove the need for shadow models, right, and you train directly on the target model, or others have been developing things like proxy models. But fundamentally, there is like a question, and this is what we wanted to look at, which is, why is that? This makes no sense. I'm giving you strictly more information. Somehow it feels like I should be getting something out of this from an attack perspective. Two? Okay. Sorry, I just need to have 2 minutes. The issue basically is misalignment. So basically here, we trained 5 models using the same 4-layer CNN. And basically every time we change different subset, model initialization, ordering of the mini batches. And basically the only thing you should see here is basically that all of the models learn pretty much the same thing, but in different orders. Right? It's the same, they look pretty much the same, but the order is very different. And this is basically because of symmetries in deep neural networks, right? So basically you have, and the main one is probably this permutation equivalent, right? It's like all of the neurons in the hidden layers can basically be switched in order, right? In any ways you want, which give you like, a very large number of perturbations that give you the same output, the same model, but just with, permutations. And the same is true when it comes to CNN with activation maps instead of the neurons. And so basically what we did, 3 things. First, identifying the key cause of misalignment in shadow models. Second, realignment techniques. And 3, given realignment techniques, went back to white box MIA, can we do better? So first, most important cause of misalignments, right? What are the differences? Why are those things not aligned? 3 things. Training data set is different. Model weights might be initialized differently, or you might have some randomness of the training algorithm, ordering of the batches, or some dropout regularization. We basically studied this by varying things, basically varying one at a time. So target models, we change the batch ordering, doesn't change too much. Dropout selection doesn't change too much. Weight initialization, basically you can see that it's more or less the same feature, but in a completely different order. Disjoint data set, same thing, probably a little less aligned, but a lot more than in the weight initialization case. So same features again, broadly aligned, right? Which basically means that the biggest, surprisingly, out of all of those source of variation and those misalignment is basically weight initialization, which is super important. We validate this by using a weight misalignment score. Basically, look at the top. This is random perturbation, and this is so much different in this. And then we vary one thing at a time. And basically, what you can see is that the biggest source is again same story. Weight initialization is what changes, particular for the first layer, a bit less for the third one. Okay. I'm being told I need to finish. So basically, we propose a method to realign the layers. We have a range of techniques. 3 to 6 basically works quite well in terms of techniques to realign, knowing where it comes from to realign. We study white box MIA in a range of scenarios, and we show that basically it gives you a much stronger attacker once you realign. So takeaways. First, we study, carefully the phenomenon of why is white box not outperforming black box as everyone would expect. We show that this is due to misalignment. We study what is the main cause of misalignment, and we show this to be weight initialization and not data sets or anything else. That has some pretty strong implications, right? That basically means that if you know the weight initialization, and in particular, if the model was fine-tuned from a base model, you might end up with white box attacks that are much stronger than the black box attack because everything has been already kind of aligned, and whatever you changes afterward is not going to really break those symmetries, making white box much stronger than model trained from scratch, which I think is a really, really key thing. And for those, in cases where adversaries, you deploy it on device, the adversary do not know the weight initialization, you can use realignment technique to improve basically the strength of attack and improve white box MIAs. And the source code is available here. I'm happy to take any question, but basically Anna Maria Cretu, my student, is the brain behind this work, and this is a collaboration between Microsoft and Imperial College. Thank you.
Are there any questions?
Hi, thank you for the interesting talk. And I might have missed something, but as far as I understand, typically we use disjoint subsets of the dataset to train the shadow models. And in one of your slides, what you were showing was that they are essentially learning the same, but if we are using disjoint sets or subsets, how can they be learning the same? Theoretically, they should be different. Each shadow model should be different, even though it's from the same domain.
Yeah. So it's really interesting, right? Because it's like basically we know that shadow models are different, right? And I think the go-to is basically to say, well, from a privacy perspective, like, oh, we don't have access to the same data set, and this is where so much of the difference comes from. And there is some difference, right? You can see here, you can see the difference when you have, like disjoint data sets, right? That has an impact on, the alignment, right? And so that means the shadow model are slightly different. But that is actually a much smaller impact than the impact of weight initialization, right? And that fundamentally it's really like you start from again, I come from optimization, right? Think of optimization, it's basically you dropped somewhere in the space randomly, and then you find your way towards a good model. And basically what this says is that where you're dropped is actually, will have a dramatic impact on the resulting model. Not necessarily that you learn a different model, but that the alignment is going to be different. As you, again, once you know the answer, it's obvious, but I think it's really important, especially when it comes to fine-tuning, right? Which basically means if I manage to get away and to solve the misalignment issue, which is typically you fine-tune a base model, which by now is a big fraction of the models, then suddenly white box attacks do not suffer from this and might very well become a lot stronger than black box, contrary to everything we thought to be true in older fashioned, not fine-tuned models, which is really cool.
Okay, let's thank our speaker once again. Let's move to the fourth presentation by Paul Gerhardt for a paper entitled Measuring Conditional Anonymity, a Global Study. Okay, let's go ahead.
Can you hear me, or do I need a mic? Oh, there's none. Oh, okay, perfect. Thank you. This is joint work with my colleagues Pascal and Dominic. Actually, I wanted to give you like a really elaborate introduction, but as we have 11 minutes, I will go the shortest one I could find. So the story of our work starts like a couple of years ago when Dominic and Pascal and me were looking into these health apps. And we are especially looking into the privacy disclosure, and we saw stuff like your data is safe. We do not store personalized data. We, of course, are comply with every like GDPR and regulation, stuff like this. Of course, we are secure by design. And my personal favorite, this is not made up. Actually, this really was written at the webpage of a health app. They say they encrypt your data using TLS. I mean, that's amazing. No, like it's encrypted, what could happen? And after you read this, you want to log in and you see, okay, there's no personalized data. However, they want to know your country, your district, gender, age, height, and weight. And we thought, okay, this cannot be true. So what's going on? So we started looking into literature, and we saw that Sweeney did amazing work and doing matching attacks. What's a matching attack? In a matching attack, you have the anonymized data set containing confidential information. This is what the app provider has. Like they do not store your identity, but they store like your zip code, your age, and your gender. and they do it in buckets. And in addition to this, they have some computational data, like your medical information, something like this. And to match this data to real identities, you need a second database. We assume that the first database is included in the second database. And what you're doing is you're looking at any person, for example, this guy here, and we're looking in our database, okay, how many occurrences of this data set do we have? And we see, okay, here are 2, though the probability that you are one of these guys is like 1/2. Same holds for like another example where we just have a single match. So we looked at this and we were like, okay, that's nice, that's great, that's a good attack. However, it's kind of hard to find the second database. What can we do against this? And we found a theoretical construct which we call conditional anonymity. So as I said, the question was how to database. What we thought, okay, the second database is kind of hard to get, so what can we get instead? What is easy to get? And we saw, okay, like basically every country has public data. So the first step we did, we used population statistic to get a rough anonymity set size. Like, as I said, it's most of the time it's like age, district, and gender, and you can really get this information out of population statistics. Then we thought, okay, this is kind of not so precise at the moment, so what can we do to add auxiliary information? And what we did is we looked further in the population statistic, and we found out that there are so many distributions over auxiliary information you can actually get. So you can refine our data set. So what we then did, we defined conditional anonymity to be the product from the population statistics multiplied with probability that you fulfill certain attributes. To be not too theoretical, let me give you an example. Okay, now in this running example, we have like population statistic and 2 attributes, B and C. And the first step is we're looking up, okay, what does the population statistic say? How many people are living, for example, in this district? And we're getting like 10 people. And then we are asking, okay, how many of these 10 people, for example, have a smartwatch? And we look into the population statistic and we found out, actually, there are statistics of how many people have smartwatches. That's public. So we found out, okay, 40% have a smartwatch, for example, and then we are going with 4 people at the moment. And then we have a different attribute we're looking at, and most of the time, these, you don't have to do so many hops to get this number really small. In a running example, it's 2. 2 really sounds small, but as we found out later, like 2 is actually like a normal number. Like when I give you a couple of attributes, you won't have a bigger set size than 2 or 3. So if we compare our approach to prior work, we have a kind of a difference. In a matching attacks, you first of all need a real database, and this database needs to be exact. And what you're doing is you're counting all matching entries. We have a different approach. We don't want existing databases, or we don't have existing databases. We don't want to real match. However, what we're doing is we're using population statistic, and we try to estimate how big the set will be once we apply all the auxiliary information, which is kind of more abstract and easier to do because this information is publicly available. Once we had our definition of conditional anonymity, we were like, okay, how precise is this? And the easiest way to do this is to get the second database I told you about and just compare conditional anonymity with real anonymity. However, as I said, that's kind of hard to get. So instead, we made a contrived country, which we call Anonland. Anonland has 102 million citizens living in all kinds of metropolis, cities, countries, areas, and villages. And we just created a contrived data set. So we have our own data set. And then we compared, okay, for each citizen, how big is the conditional anonymity set and how big is the real anonymity set? As you can see in my chart, do you see my mouse? Amazing, yeah. As you see in my chart, like that is the real anonymity we were expecting, and the conditional anonymity is like a collar around this. Like it's a rough estimate. However, it's like kind of a good estimate if you see in here, like it's a bit deviant from it, but I think it's basically the same. So once we compute the conditional anonymity, we are quite optimistic that your real anonymity is not far away from this, which is good for us. That was our first step, and then we were like, okay, now let's get population statistics. So what we did is we wrote an email and we visited all kind of web pages and asking governments and census bureaus, okay, guys, can you send us some data? And actually this worked quite well. So at the moment, we have the data of over 1 billion people all around the world. It was easier to get it from the EU, Australia, and Northern America because they answered in English, kind of. And like we got all kind of like interesting results from all different countries. And if you are living in one of these countries, which is not green at the moment, it would be amazing if you can, maybe if you have some time, you can get your population statistics, send it to us, and we are happy to include it to our data set. So we can visualize this for more people. And I have one fun story I want to tell you, which was my data response I got like 4 weeks after I sent the email. First of all, I thought, okay, that would be spam. I mean, that's a bit weird, no? And then I opened up the PDF and I saw the Russian government actually answered to my call in a Russian document which is typesetted and you cannot copy out of it. Google Translate did a great job, and I had a friend speaking Russian, so they tried to explain me how to get the data from the web page. However, this did not work. And funny about this is a thing above here, like this is it's a political officer signing that this information is actually, like you can give it out to the German university, which is kind of fun. Unfortunately, I did not get any response in English, and I wasn't able to download the data from the web page. But we got a response. So what we now have a big data set, we have conditional anonymity, and now we thought, okay, let's do something with it. So we conducted some kind of case studies. So first thing we looked at was the US. We computed the average conditional anonymity set size for each county in the US. And on average, it's 77, which is quite okay. You know, like 77 with like 5 attributes, that's not too bad. And then we looked into the map and saw, okay, it's basically red, except for California and maybe Boston, Florida. So and what we saw here, that the average conditional anonymity set size, it's not the minimal, it's the average one, it's like 2 in all these countries. And then we looked a little bit deeper and we saw, okay, the conditional anonymity set size is below 5 in 97% of all countries. And if you remember to my introduction, like I only asked you for like 5 information points, and these are only in buckets. It's not precise, it's like between 20 and 25, for example, or hate between 160, 165. And even in these buckets, yeah, I mean, you're like below 5. So if you give me this information, you're not really anonymous. You're kind of in the group of 5. And if I'm like a really motivated police officer, I will find you, I guess. I hope at least. Then we looked into evaluation apps because of the Roe versus Wade thing in the US. And we found out that if we know that you're using the Flow app, it's even worse. Like from 77 we had before, it's now 20 in the US. And as a little reminder, it's an average just 5. And you can see in here that really, like this one more auxiliary information really makes your conditional anonymity really smaller. Then we did not compare just single countries, but we compared different countries with each other, and we found out that in Australia, in Acton, there's just 1 male in his anonymity set size, and that's not even having his height or weight. It's just because there's basically like 1 50-year-old guy living in Acton. And that's because in Australia, all the zip codes are so small that only knowing the zip code is kind of a privacy violation. Then we looked in like gender-specific differences, and what's interesting in Hong Kong, if you are male, your anonymity is much better than a female. So that's kind of. And then we were like, okay, now we have these case studies, we have all the theory, but we want to educate people that this is really a problem. What can we do? What can we provide? And what we did is we created an online tool which we call Visual Anon. And the idea of Visual Anon is that you can do your own case study with your own data just on our homepage. So what we are doing is, like this here is a small example. In Visual Anon, you can insert all your information. And having your information, we will calculate how big your conditional anonymity set size is. No worries, this is not like, we don't store any of your data, of course not. And it's secure until less, you know. And so in our running example, we again go to Australia because Australia is a fun example because these zip codes are so small. And we have roughly 27 million people living in Australia, and we chose the district Abbotsford, which has like roughly 8,000 guys, and 4,000 of them are male. And then what you see is we have also like this statistics in here where we just plot what's going on. If you're getting older, for example, then it's getting better, or it's worse actually if you're getting older. So it would be really good if you would be like 25 or 30 if you live there. Then we have the height and weight distribution, and of course, like if you're 175 big and you're like 85 kilograms, the probability that you are in a bigger group is like higher, of course. But if you're like really small or really big, and then your probability gets lower. And then in the end, if you insert all your buckets you have, all your attributes you have, you see in the end like there are 3 guys in Abbotsford that are male in this age group with this information. And I promise you, if you do it for your own data, it will be kind of small. Like it's super interesting to see how fast it gets smaller. So I want to conclude my talk with one thing I want you to remember afterwards. If you give out your socio-demographic data, you are not you are really de-anonymizable. Like you should be aware of what you do with your data. And if you want to estimate how de-anonymizable you are, just visit Visual Anon, and I will show you. And here's the source to my paper, or to our paper, and to Visual Anon. Thank you.
Thank you very much. Are there any questions to the speaker?
Thank you. I'm curious, you seem to take an approach that you don't want to build any statistical or like machine learning model to try to do this extrapolation. But eventually you're gonna hit a limit of scale when you want to like model these things because you don't have access to a lot of information. So if you don't have access to the proper cross tabulation you want, if you just have access to like three-way table from census data, etc., eventually you do need to build a model to account for like, I don't know, higher level association or thing like this. So
yeah, actually,
there's a limit. There's a hard limit on like what sort of things anonymity set size you can measure if you don't want to use statistical models.
Exactly, yeah, we are relying on statistical data. It's interesting what is actually measured by the census. Like they are really measuring much things. And as we saw that is if you have like three or four attributes, it's already like so small that everything just works. For example, we really had this auxiliary information, how many people are using smartwatches in Germany. Like the German census is really computing this. And if you look in our paper, it's like interesting to see like we had a case study with the COVID app of Germany, and we saw that if you're in Germany and we know that you're using this application, like your anonymity set size is 1 basically, and if you know that you're a smartwatch user, it's actually make everything worse. But we did not want to use any machine learning stuff because we want to make it as easy as possible so everybody can just see what's going on.
Okay. Any more questions? Okay, I should be able to provide you with some source of data from Saudi Arabia.
That would be amazing,
Yeah.
actually. That would be cool.
Yeah, it's one of the dark areas, and I'm aware of some public sources, so I will email you with that. You are welcome. So let's move to our final and sixth presentation by Sebastian Lenzner for a paper entitled Decision-Based Data Distribution, Enabling Users to Minimize Data Propagation in Privacy-Sensitive Scenarios. Okay.
Yeah, thanks for the introduction. This is a joint work with my colleagues Kilian Demuth, Marc Fischlin, and Christian Reuter. And our work is motivated by the fact that some companies share their secret keys with middle boxes or firewalls for malware checks, but this ultimately weakens end-to-end encryption. And on the other hand, client-side encryption has usability issues. According to Google, for instance, encrypted emails cannot be used for search options or malware filtering. And our approach aims to use layered encryption to provide a trade-off between privacy and usability. Users can decide which information is sensitive and add an additional layer of protection to it, and all non-sensitive information is transferred as usual and then can be used for search option or other things. To go more into detail, we're utilizing the stealth protocol from Fischlin, and that basically allows us to generate two pairs of keys in one single TLS handshake, while providing the deniability to an attacker that can monitor the network traffic, that he cannot distinguish whether the second key was generated or not. We have several assumptions for this model. We assume that there's some kind of email client or email client extension or even mobile app to provide the ability to store the keys and process them, and also have an authentication mechanism attached to it so that the user can be identified. The reason behind this is we want that no sensitive information is stored in plain text, and the user has to be authenticated within the app, and then manually decide to decrypt the data so that it's temporarily available. The overarching use context of our system is online forms, because many companies and organizations already use them, and the backend could be changed. From our pre-study, we derived that the most utilizable use case would be the communication with medical offices. So we designed two demonstrators, a non-customizable version and a customizable version, to get some insight on the control paradox. First, we see the online form for the non-customizable version, how a patient would see it. It's just some personal information text, how the system works. And then there are two input fields. One is without additional protection, and one offers additional protection for sensitive information. This is a view for the doctor. It's similar. The doctor can see the patient data, has a different information text that says that the highlighted information is considered sensitive by the users and therefore should be used with care. First of all, because the user is very concerned about this, and secondly, this information is not checked by firewalls, so if there's a link or something in it, treat it with care. And thirdly, this is the answer that the patient receives. And as you can see, the sensitive information is not displayed. It's hidden behind a button in this case. And we assume that when the user is authenticated and then decides to decrypt the data, it's temporarily decrypted and shown, so that even on the on device of the user, the sensible information is never stored in plain text, just for use cases like shoulder surfing or shared devices. On the other hand, this is the customizable version. As you can see, the second text area is missing, and the controls are moved to the right. So the user can decide for every piece of data if it should be only visible for the doctor or if all the other staff members can see it. Again, this is the doctor's perspective, and again, the sensible information is highlighted. And again, the answer shows only the non-sensible information, while the information that uses the additional encryption is not shown. We then conducted a qualitative user study with both demonstrators. We interviewed 42 participants and with hands-on experiments on both demonstrators. And here are some selected results. First of all, what are the reasons why users prefer the non-customizable version? Users said there was the possibility to misclick in the configurable version, and that making those decisions would cause overload. Some said that the separate input fields for the non-sensitive and sensitive information would provide a clear separation, and this would be intuitive for them. Some favored that there were less clicks, and many were really curious to hide too much information. They were afraid in the customizable version that they would protect information that would be actually usable for staff members to process the order, and that by encrypting that data, their order or the request might be delayed or even failed, and it would be a burden to staff members. On the other hand, these are the reasons for preferring the customizable versions. Again, some people perceive this as intuitive and fast, while perceiving the non-customized version as cumbersome because there are two tags for different addresses, and it was perceived redundant. And some were afraid that if they perceive the two input field, then data could be leaked unintentionally. Therefore, they thought the customizable version would offer better guidance, and even the possibility to hide the personal information, which is not possible in the non-customizable version. Furthermore, we saw that the mental model of the users were affected because due to the option to customize their privacy, they had the feeling that they are giving the data away voluntarily, while in the non-customizable version, they had the feeling that the data is extracted from them, that they are forced to give it away, and just by having the choice, they had a better feeling. And we also received the feedback that the overhead for clicking the checkboxes would not be a hindrance for usage. One of the main benefits of our solution is that there's increased privacy at home and in the medical office. By not showing sensitive information, problems like shoulder surfing or shared devices are addressed, and we investigated which use cases might be especially relevant for this protocol. First, I'm going to present the use cases for the increased privacy at home. What often was mentioned is that in the medical context, a patient might receive severe diagnosis like cancer or other lethal illnesses, and that they want to cope with this diagnosis and process it themselves before then deciding if and with whom to share it. And our mechanism would help them by hiding this information from others. The next reasons could be categorized as housing situation. For example, if there's mistrust at home, or if parents want to protect their children from the diagnosis they are getting, or if children want to be protected from their parents, especially for young women, it is a problem because some participants reported that they had a hard time getting to the gynecologist at a teenage girl because their parents didn't believe in this. So it was very hard for them. Then there is the issue of shared flats, where maybe also devices are shared, or shoulder surfing is an issue. One participant mentioned that if someone has a divorce but they're still living together, this is also a good use case for increased privacy. And four participants also mentioned domestic violence. The next topic is intimate topics, revolving about pregnancy, planned or unplanned, getting results from the urologist, which could be very sensitive, or abortion. Then there are taboos and stigmatized topics. Most participants just said there's a general topic, but some were more specific by mentioning sexual transmittable infections or psychological issues like depressions. There also was concerns about drug abuse, including alcohol, or even help for suicidal people. Some participants also mentioned the fear of discrimination. As one participant stated, it contains everything that would prevent him from living on his life as he lived before. Some others were more specific, like LGBTQ topics or disablement. Other reasons could be categorized as school topics, for example, protecting the communication between teachers and parents, or pupils and teachers, transmitting legal documents, or some state and religious reasons where maybe they cannot talk with their families about their beliefs, and then they want to have a secure communication with someone to give them advice. Next are the use cases for the increased privacy in medical offices. And again, this resolved about sensible topics, like intimate topics, psychological issues, or taboos or stigmatized topics. And another big topic were social aspects. Many participants mentioned that living in rural towns or areas where everybody knows each other, it's sometimes hard to go to the doctor because you are seen, and then people might spread rumors. And one participant even stated if that her grandfather is not going to the doctor because he's so afraid of the rumors. Then the next point is that relatives or acquaintances might work within the medical office, which is a huge issue for many participants. And one participant even stated that if he knew that someone he knows worked there, he would go to a different medical office. Of course, this is a luxury that everybody has. And then there is the fear of using the telephone. This does not only include the telephone anxiety, but also the fear of eavesdroppers. For example, if you call a medical office and the person at the front desk picks up, and then maybe they talk to you, and there's personal information or information about your health status leaked, and other patient may eavesdrop on it. There was one participant that stated that a friend of hers stated her name and birth date at front desk, which is usual in Germany to identify a patient. And this information was observed by a bystander, and this person then used the information to find her on social media and contact her. To conclude, in our paper, we presented a design for an interaction concept that increases privacy and enhancing communication in C2B scenarios. We utilize a stealth protocol to achieve deniability of key creation, which could be relevant for sensitive use cases where the communication has to be hidden. The solution is suitable for different use cases, and we investigated on a specific use case, the use case of medical offices, and we showed that this tool can reduce social barriers to seek help, and even the form-based communication is an improvement to the current status quo. One particularly interesting finding is that giving control to users affect their mental models and thus the way they disclose data, which could be contribute to the discussion around the control paradox. Because users feel not forced to give the data away by feeling in control, they deliberately give the data away, or as some of our participants stated, everything they did not encrypt, they decided not to encrypt. Our study is subject to some limitations. First of all, not all findings are exclusive for our solutions. There might be other solutions that achieve the same things. But we can show that even those people who do not care about the privacy or never even thought about it have benefits by using our solution. And our evaluation was of qualitative nature, which means that it's not necessarily representative for all populations. With this, I want to conclude my talk, and if you're interested to play around with the demonstrators or modify them for your own purposes, feel free to use the QR code or approach me here at PETS. Thank you.
Thank you very much. Are there any questions? Okay. I have a question for you. What next steps for this research you plan to take?
Yeah, this was a first step of creating the concept and asking users if they're actually interested in it. We were considering doing implementations or going to experts, but we discarded that because doctors, lawyers, or social workers are very busy, and it's quite hard to get to them. And when they offer their time and work for a study, and then we implement it and make a tool, and then we see the end users don't want it, then it was all to waste. So this was the first step. And one of the next steps would be going to the experts or professions that handle sensitive data, or companies that are afraid of data breaches and want additional protection. And yeah, so follow-up study with experts, and implementations for different use cases depending on the expert interviews. And yeah.
Okay, thank you.
Encrypt for a doctor's eyes only, then you would need to know exactly which doctor you want to visit or contact. Is that right?
This is the reason why we have the overarching use context of online forms. First of all, online forms are structured data that allow easily for taking parts of it for additional encryption. And the vision is that there's some kind of editor that every doctor, every office, every company can design own forms for their website. Many already have web forms on their websites that can be utilized. And as you can see in this, for example, here, in this form, we had an option where to choose the doctor. In Germany, it's the case that sometimes there are medical offices where multiple doctors are working, and usually a patient has one doctor that is the main doctor as a Hausarzt in German, and you can select them in this form, and then the keyword generated between the two. Does this address the question?
Okay. With that, we conclude this session. I thank all the speakers, and I thank all the attendees for their time. Thank you very much, and see you later.
I'm going to give it another couple of minutes so people have the possibility to make it here from the lecture hall. I know officially we start at 4:30, but that's just not organizationally possible. So, well, at least not without people running into his talk all the time. Yes, I'm absolutely aware of that. So there should have been at least a 5-minute break. All right, let's get started then. A bit late, but yeah, we might also still have a couple of people. So let me give it another 1 minute. That seems like the current stream of people has stopped, so sorry for making you wait so long, but at least now you should have a quiet room. This is the last session, so you probably all know how this works. We're going to have a couple of talks, and we're going to ask a bunch of questions. So without further ado, Sitchin, take it away for the first paper.
Thank you so much. Hi, everyone. Today, I'm going to present the paper, Understanding Leakage in Searchable Encryption, a Quantitative Approach. This is a joint work with Sasha, who is here, and also Bogdan. So this work is a very theoretical work, but I hope I will keep it high level so that you won't fall asleep in the middle. So let's start with a quick introduction to searchable encryption, because I believe that not all of you know about this topic. So in searchable encryption, we consider two parties. There's a client and there's a server. The server is honest, but curious in most of the settings. The client holds a set of documents. These documents, you can think of them as a set of emails and so on. Usually what happens is that the client is going to index this set of documents so that the client can search over the documents. But you don't want to just store that locally because that costs storage on the client. So instead, we want to have a mechanism to allow the client to outsource that inverted index to the server in an encrypted form, of course. So after doing all of that, the functionality we try to achieve is the following. The client is going to generate some kind of query with some kind of keyword. In this case, this is going to be encrypted, sent to the server. The server does some kind of computation. And by the end of the computation, the server is supposed to return the documents that match the query. But in the simplified case, we don't consider the document retrieval, but only the index retrieval, meaning that by the end of the query, the client only gets the document identifiers of the documents, but not actually the document content. That's sufficient for this talk. So of course, this is a privacy, for this kind of protocol, privacy is important. In this case, we care about the privacy of the actual data and the queries themselves. Okay, so privacy is important, so definitely we have a security notion for that, right? So we have a standard security notion for that, and it was proposed in 2006. So it's been almost 20 years for this security notion. So to give you a kind of high-level introduction to what this security notion is, it's a simulation-based games. So there are actually just two games. There's one real game, and in the real game, it's a real execution of the scheme where there are two parties. One party is the game itself. The game acts as the client, and here the client has secrets. And then the other party is the adversary, and the adversary plays the server. So you can imagine that in this interaction, the server is going to observe the transcript of the whole execution, right? Then we have another game, that's the ideal game. And in the ideal game, it's a simulated execution of the scheme. And by simulation, I mean that the adversary doesn't really interact with the scheme itself, but it interacts with a simulator that has access to the leakage of the real data and the queries. Okay, and the server and the client plays the same roles as before. And crucially, if you can prove that the real game and the ideal game are indistinguishable, then we have the standard security. And intuitively, what that means is that if the attacker, the adversary in this case, cannot distinguish the two games, then the adversary cannot learn more than what the leakage entails. So that's pretty much it about the standard security notion. And if you are curious how it looks like, concretely, it looks like something like this. You have a real game on the left, you have ideal game on the right, and they are computationally indistinguishable if you can prove the security. If you follow now that, at least one thing you should remember is that security is quantified by the leakage function. As soon as you show that you have this leakage function and the two words are indistinguishable, you have security. I will say that if everything really works out, then that's the end of the talk, nothing more to discuss here. But unfortunately, that's not the case. And there's a lot of problems with the standard security notion. So let's dive right into that. So there are mainly two issues with the standard security notion. The first is that leakage functions I've just described to you is often very, very complex. Maybe you have a background in MPC, and you know that there you may use a very similar kind of security definition, and there the leakage function may just be something very naive. It can be just bot, meaning that there's nothing is leaked, or it can be the size of sets in a PSI protocol, right? So that's very naive, but let's see what you can get in searchable encryption schemes. It's something that's pages long, and it's very hard to decipher what that means. So, okay, if you have leakage functions, they are long, what does that mean? Probably you still have a security proof, so maybe everything is secure, but unfortunately that's not the case. These leakage functions can really be exploited, and they have been exploited time and time again. And if you want an example of that, look no further than the next talk. Right? If that's not enough for you, then here's a list of 10 more attacks. And these attacks don't only apply to one scheme, two schemes, they actually apply to thousands of searchable encryption schemes. And that's where the problem is at. So in summary, what I've told you so far is that a security proof in the standard security notion, in the standard security model for searchable encryption, does not imply privacy of data or queries. And that's the problem. So now, knowing that, there are really just two options, right? One option is that we are just going to accept the fact and design schemes that actually with very little leakage, and you can say, yes, these schemes are secure, but this is not very, very easy. So here is an example of a scheme that has very small leakage. I want you to pay attention to the third row and the last column and the third last column. The numbers you see are the communication costs of a standard encrypted multi-map, which is kind of searchable encryption scheme with a lot of leakage, and then a scheme with minimal leakage. What you see there is that the communication overhead by using a scheme that has very little leakage, which is the third last column, is really, really high. Here it's 180 times. So you don't do, it's very hard to get a scheme with small leakage. Right, so we really need the alternative approach, which is we design schemes that are efficient, but with some kind of leakage. Then we try to argue that that leakage is harmless, or at least it doesn't lead to devastating attacks. So there's been a few attempts at this, quite a few, in fact, and they can be categorized into a few categories. But in the interest of the time, I'm not going to go through all of them. But you're welcome to read all of them on your own. So let's quickly go through what we have done in the paper on a very high level. So our work is actually inspired by one of the previous works on quantitative information flow. And what we have here is a very similar approach. So our security is going to be quantified by a leakage function. And the leakage function looks something like this. It has 4 components. The first component is the function itself. It's a functional description, right? So, and this description is known to the adversary. Then the second component, the W, is actually a guess made by the adversary. And the goal of the adversary is actually to maximize this function, right? So, and the last 2 components in this case are information known by the game. DB here refers to the database itself, and the Q with an arrow on top refers to the set of queries. As an example of quantitative information leakage function, we have a function that is 1 if the guess is equal to the database and 0 otherwise. And this captures the class of attacks that corresponding to database reconstruction attacks. So we can use this function to capture a lot of different classes of attacks. But I don't actually have the time to describe to you how we actually use this function to construct our security notion. But instead, I will just give you a comparison of what can be achieved with the standard security notion and our security notion. So we'll have a few criteria. So the first one of those is what do you quantify the security notions over? In the standard security notion, it's quantified over the leakage function. And in our notion, it's quantified over the quantitative leakage function. Although both sounds like functions, they are actually very different. Okay, so here the goal for the adversary in the standard security notion is just to distinguish the real game from the ideal game. Nothing more than that. But in our security notion, we only have 1 security game. There's no 2 games. And in that game, the goal of the adversary is to maximize the quantitative leakage function. Finally, one more, there are 2 more things. One difference is that in the standard security notion, the output of the game is just a bit. In our case, it's a real number. And finally, the security guarantee of the standard security notion is nothing because we don't know what that leakage translates to. But in our case, we can actually show that if the output is small enough, then we can show that the scheme is secure against a class of attacks. With that, I'm not going to show this. With that, it comes to the end of the talk. If you're interested, you can scan the QR code to read the paper. Thank you.
Thank you for the talk. So questions, great.
Oh, thank you very much for the talk, very nice. So your quantitative leakage function, is it like the G vulnerability from KIF, or is it?
Yes, it's very similar, but slightly different because in the G leakage, if you remember, you have a source, you have an output. You only have 2 quantities, but in our case, you have more than just 2 quantities. If you look at this slide, you see the guess itself, you see the database as a component, you see the queries as a component. So the guess has more freedom in some sense.
Okay, so it doesn't really this do not really play the role of a channel, right? The database and the queue.
It's similar to a channel, but in this case, it's more complicated because in a standard channel, you usually just model the input and output as random variables, and that's it. But in our case, there's a lot more going on because you are running a scheme on top of these random variables in some sense.
Lovely, nice, yeah, brilliant. Thank you very much.
Thank you.
This might be a bit of a dumb question, but do these new defined security notions have any correlation with forward and backward privacy, so to say, and searchable encryption?
Yeah, thank you for your question. Well, in this case, we don't actually consider forward and backward security specifically, but they actually can capture those attacks with the leakage function quantitative leakage functions themselves, right? Because you can say that, okay, so for example, you know how that works, so I don't need to explain that.
We would have time for one more really quick question. Okay. And let me ask one. For whom is this defining the leakage function made? Because I think a cryptographer can properly do that. But if you give the real number to a developer, that might not be that useful either, right?
Yeah, thank you very much for the question. We actually have a whole section discussing how to pick out these things in our paper. So really, this is not a job for the developers, it's a job for us.
Okay, good.
Yeah.
Thank you.
Thank you.
Okay, then the second speaker. And thank the speaker by standing up. Okay, so our second talk is by Karim on Markov process leakage. Take it away. Floor is yours.
Thank you for the introduction. So my name is Karim, and I'll be presenting our work, Maple, which is a Markov process leakage attacks against encrypted search algorithm, which is just, you can view it as an extension of what Zishan just explained. So how do we leverage leakage in order to mount an attack to gain more information about the queries and also the plain text data? This is a joint work with Celine Kamara, Tarek Motas, Jamie Di Maria, Andrew Park, and Amos Tribe. So the agenda of this work would be basically me trying to motivate a little bit the need of for encrypted search, then a high-level overview of encrypted search algorithms. Then I'll pass to explain what are leakage abuse attacks against encrypted search algorithms, and then dive a little bit deeper into our two attacks, mainly attacks against the query equality leakage pattern in the dependent setting. And then I'll just gloss over some of the summary of our results, explain what the data sources that we used, and also the evaluation scenarios, and give you guys some key takeaways. So as you all guys know, in the past couple of years, data breaches has proliferated, and we are going to see, for example, each week some headlines like 10 billion passwords have been leaked, or for example, the mother of all data breaches where 26 billion records have been leaked, etc., etc. And this kind of leakage or data breaches affects a lot of companies and also users, and some of them are major companies, for example, LinkedIn, Adobe, Tencent, Weibo, X, among others. So the general idea, or ideally what we would like to do, is to have some kind of cryptographic mechanisms on top of our data prior to outsourcing it. This would save basically our data in the case of a data breach or a data leakage. But in the same time, if we just put a normal kind of cryptographic mechanism, we would lose our computational complexity over the data in the server because it's encrypted, and we can't just keep downloading our data each time that we want to execute some sort of computation over our data. So here comes to play encrypted search algorithms in general. So what is encrypted search? It is a research area that focuses on the data design, analysis, and implementation of cryptographic primitives that allow the user to query their encrypted data privately and also efficiently. At a high level idea, I won't go over a lot of the details since Zichin already did that. So we have like a trusted client that would like to outsource their data. They can generate an inverted search index and then outsource the data to the untrusted server. And at any point in time, we can generate variable types of queries, either keyword queries, range, and other types of queries, and the server will send us the matching records to the client. And however, most efficient encrypted search leakage algorithms or schemes leak some form of information through the setup and also while executing the queries. And this is for the static data structures. And also we leak more in case we have a dynamic data structure, where we can leak also the update and delete histograms. So for our work, we are mainly focused on a leakage that is commonly associated with structured encryption algorithms, where we have an attacker or an adversary that tries to mount an attack, given auxiliary information in some leakage to gain either the queries or retrieve the queries or the plain text data. And our adversarial model is a passive and persistent adversary. This adversary is basically, you can view it as has access to the transcripts of the execution of the protocol, but won't deviate from the protocol specifically or try to inject some kind of information. And given the fact that leakage and auxiliary information heavily influences the recovery rate of the leakage abuse attacks, I'll try to explain what is a leakage profile and explain why did we specifically pick the query equality in the dependent setting. So a leakage profile is a set of one or multiple leakage patterns. For example, we can have the response length or the query quality, coherence metrics, among others. This is not a full set of all the possible leakage patterns, but just to give you a high-level idea. And we picked the query equality leakage pattern in the dependent setting because first, query equality is a leakage pattern that is leaked by most PPE and SSE-based schemes. And also it hasn't been properly studied prior to our work. And we picked specifically the dependent setting because as a human, we are most likely than not to generate queries dependently. So let's say a person is sick or has a stomachache. The first thing that you would do is look up their symptoms online and then try to find the nearest doctor, let's say, for example, a gastrologist in their area, or maybe if the symptoms are not that severe, they'll just try to look for some remedies, etc., to stop pain. So our main research question that we try to solve using our paper is this. So given observed leakage in a non-query distribution, what is the query sequence that is most likely to explain this leakage? And we try to do that given this adversarial model. We have an adversary that has access to the query sequence or the query distribution as its auxiliary information, and then the query equality pattern as some observation. Then we formulate our query recovery as an uncovering problem, and we use solutions from existing literature in the stochastic processes. Mainly, we model our query distribution as a first-order Markov process, Markov chain, and we use transition matrix, initial distribution, and stationary distribution as input for the Viteri algorithm to solve this kind of problem. And to give you guys a high-level idea of our contributions, we proposed two new attacks. The first one is the stationary, which you can view it as a frequency attack, where we try to basically match the average number of visits to the closest number or value in the stationary distribution. At a high level, this is a mapping of every query to its corresponding keyword using the convergence of the average number of visits. And for our second attack, we use the first attack as a warm-up and then execute an inference attack where we model the user's query distribution as the hidden Markov chain from a hidden Markov model, and then the corresponding leakage as the observable process. More specifically, I'll just try to explain at a high level the steps that we do for our first attack. So the first step would be to compute the stationary distribution. Then we calculate the histogram of sequence of queries. And finally, we try to map the closest value in the stationary distribution to the average number of visits for all states. And also, our algorithm also outputs an error, which is the total distance between the average number of visits and the selected component in the stationary distribution. And as I just described in the previous slide, we use the first attack as a warm-up for our second attack. So from lines 1 to 5 in our pseudocode, it's just trying out first attack. And for the second step, we compute the observation matrix from the hidden Markov model parameters. And lastly, we try to give given the hidden Markov model in the observed sequence, we can run the Viterbi algorithm, which outputs the most likely sequence of visited states in the hidden process. And also we output an error score, which is used to quantify the quality of our mappings. And finally, to evaluate our attacks, we use two kinds of distributions: the real-world query distribution based on the AOL inter datasets. And we also designed 4 evaluation scenarios. The exact scenario, it's a scenario where the adversary has access to the exact query log of the user. And the all scenario, it's another scenario that's more similar, but where the adversary has access to the query log of the client among other query logs. The split scenario, we give the adversary half the original query log as training data, and the other, we basically have a set of query logs excluding the one that we are trying to attack. So you can view them as the first 2 evaluation scenarios are the most unlikely or most unlikely scenarios to happen in real life, but the second 2 are the most true to what would you guys can face in reality. And since we know that both our data sets can't cover everything, so we also try to execute our attacks over artificial query distributions, mainly for uniform zip and binomial zip and zip, where we varied the sparsity of the transition matrix. And I mean by that we varied the Hamming weight, which is just the number of outgoing edges from each given state. Finally, I'll just gloss over the summary of our results. As you can see, our attacks achieve a higher recovery rate for the first 2 evaluation scenarios, but none of the attacks really achieved anything or like recovered anything for the second 2 evaluation scenarios. And this was true for both the AOL and TED datasets. And this is given like the aggregation of the evaluation or the evaluation and result of our results over 5 users. Similar conclusions can be drawn also for the artificial distribution, where basically we had near perfect recovery rates if we fix the Hamming weight. And I mean by that, if we fix the Hamming weights to 2, which is basically we are having a sparse the transition matrix, and we varied the sequence length of the query sequence. But in the case where we varied the Hamming weight or we had a more dense transition matrix, our recovery rate like started to drop tremendously to the point that we couldn't recover more than 15% after 100 with the Hamming weight equal to 100. And similar conclusion can also be drawn for the remaining artificial distributions, the binomial zip, uniform, and zip, etc. And to conclude, I would like to say that the recovery rate of existing attacks depends highly on prior assumptions over query and data given specific leakage profiles. And despite outperforming the state of the art, it is fair to say that none of the attacks really worked in a more realistic setting, and the computational overhead of all of the attacks, ours included, is really prohibitive in practice. And this can be seen basically here, where we varied the query sequence length. So once we started reaching like 1,500 states per query sequence, we couldn't basically evaluate our data because each data point took us at least 4 hours to evaluate one data point for given like a high-level servers, basically. And finally, I would say that it remains open to find attacks that work where the attacker does not know the exact query sequence of the user. Thank you so much, everyone, for listening. And for more details, please check our paper.
Thank you for the talk. Any questions? Should I start with one then? Well, let's start with a simple one. Why did you decide on a first order Markov process and not something else?
We can use anything basically to model our query distribution. We just picked the Markov chain of the first order because it was like the simplest kind of Markov process to do. But also we tried to have as little information for the adversary as possible. So that's why we picked an adversary that has knowledge on only the previous step instead of having multiple steps. But it is possible to modify our results and have like a Markov chain of order n.
Okay, any more questions? No? There you go.
I was curious, following this. Of course, if the overhead is already huge, this is mostly theoretical, but do you think it would change a lot if you have like a second, third order Markov chain? Do you think it would be much more effective or kind of
we tried, when we were having our evaluation, we tried for the second and third orders. We didn't see much of a change, at least based on like a small query sequence. So we've already reached a high level recovery rate. So we had like 100% in sometimes, and sometimes 90%. So the average would be like at least 70, as you can see here. So, but the problem that we faced is basically the longer this query sequence, that's the bottleneck that we faced. The longer the query sequence, the more problems we had. And most of the previous evaluations of previous work stopped at just 500. So we were the first ones to like extend our work to more than roughly 2,000 query, the query sequence of the size of 2,000 states. So, yeah, sure.
Thank you. And next speaker can already set up while we thank him for the nice talk and the answers to the questions. All right, next we have Christian talking about plan. Floor is yours.
Thank you. Yeah, I'll be talking about our work, which we titled Plan, on variance aware private mean estimation. And here at PETS, we of course know that privacy can mean many things. So specifically, when I talk about privacy in this talk, it'll be about differential privacy. And I'll just start out with some of the tools from differential privacy that are needed to follow this talk. So sort of informally, one of the ways we can achieve differential privacy is that instead of releasing some query output exactly, we'll add noise to the query. And the idea here is that the distributions should not depend too much on the individual, on any individual's data. And I have a sort of a small example here where the true input will be either 0 or 1, depending on some of your sensitive data. And then if I can only observe the output after adding noise, then I can't be sure if it's from this red or blue distribution. And there are two concepts from the field of differential privacy needed for this talk. And one is that privacy in differential privacy is quantitative. So if we add more noise, then we get stronger privacy guarantees, simply because the distributions are then even harder to distinguish. And then the other thing is known as sensitivity, meaning that depending on how much the query can change also affects our privacy guarantees. So apart from this example with 0 and 1, there's another example where the true output is either 0 or 3, depending on the sensitive information. And now it's much easier to distinguish the distribution, but then we can mitigate this by increasing our magnitude of noise to get strong privacy guarantees again. And the problem we want to solve here is mean estimation. And the idea is that we're giving a data set of n data points, and they are encoded as some d-dimensional vector, where each vector corresponds to some features describing one individual. And then we assume that the data points are from some underlying distribution, and we want to estimate the mean. This is a common task in data analysis, and in particular in statistics, where we don't assume that we can gather the information, the statistics of every individual, but then we use that to estimate something about the population. And if we don't have to think about privacy, then the typical way to solve this problem is to report the empirical mean. So we have this data set, and we just report the average of all the vectors we have in the data set. And then the question is, why is this interesting from a privacy perspective? Well, it's because the empirical mean can reveal some information about individuals if we sort of can track things over time, for instance. So here's a small example where the empirical mean is marked with a cross, and I have some data points. And then I, as an adversary, might know what the empirical mean is of my data set. Then someone else's data is included in the data set, and I observe the new empirical mean. And even though I only saw these aggregate queries, I can infer exactly what their input was, because now the mean moved a lot. And this is particular can be an issue if for outliers in the data set, that they will be easier to detect. So how will we mitigate this from a privacy perspective? Well, instead of releasing the empirical mean, we want to estimate it, and we'll be doing so by adding noise to every coordinate in this data set. Every coordinate of this empirical mean. And now our goal is to minimize the expected distance of our private mean to this empirical mean, while still satisfying the privacy constraints, of course. So what I want to present is more the core idea of sort of our technique compared to previous work. And we focus primarily on what we say are skewed distributions. So that would be some distributions where some coordinates vary quite a lot, while other don't vary very much. And here's sort of a simplified example in 2 dimensions where we say that all data points come from this gray box. And one of the standard techniques in differential privacy is called the Gaussian mechanism, where we add the same or noise with the same magnitude to each coordinate from a normal distribution. And this is sort of visualized with this brown circle. And the problem for this kind of setting that we're interested in is that this technique adds way too much noise to the small coordinates. So remember from the previous slide that if coordinates differ a lot from adding an individual, we have to add more noise. But in this case, even though the y coordinate doesn't really differ a lot, we have to add a lot of noise to it because the x coordinates differ using this technique. And we get a particular error here. Don't worry too much about the particular error, but just know that the problem with this approach is that we add way too much noise to the small coordinate. So then an alternative technique we could use is to scale our noise proportional to each coordinate, so that we add more noise to the large ones and less to the small ones. And you can see here, if we scale linearly to how big the coordinates is, then we add way less noise to the small coordinates, which is great. Now the only problem here is that now we add way too much noise to the large coordinates. And it actually turns out for the error metric that we're interested in, that we get the exact same error as we did for the other ones, that everything we saved for the small coordinates was sort of paid for with the large coordinate. So our technique uses sort of a middle ground, which you can see by this blue ellipses, where we add less noise to the small coordinates, but we don't have to pay the entire cost for the large coordinates because we don't decrease it as much as the other approach. And this is sort of tailored towards our specific error metric. And this is sort of the core idea of what we do compared to what previous work has done. And in this simplified setting where everything comes from this box, the error now scales with what is known as the L1 sensitivity. And just to compare it to the 2 other approaches, we can say that it's never worse, but it will be better. And then how much it improves depends on how much skew there is. So if all the coordinates are roughly the same, then we'll perform roughly the same as the other techniques. But if there's a lot of skew, so we have a few large coordinates, then we can save quite a lot. So that's sort of the core idea that we use in our algorithm. And just want to go through sort of a very high level what is the ideas of how our algorithm works. So we start out by having the original data sets, and here the star marks the empirical mean, and which we cannot release due to these privacy reasons. And then our technique sort of recenters the data, so we get some rough estimates. I don't really have time to discuss the details here, but the idea is that we sort of move the data based on some bad estimates, but it allows us to add less noise later. And then we scale our data based on this approach from the previous slide, where we want to add less noise to small coordinates. then the next step is to clip the data points to a certain length. And this is a very standard trick in differential privacy because this allows us to eliminate outliers. If there's a single point that is very, very far away, then we clip it so it's much closer to the center. And then we add noise, sort of using a standard differential privacy technique to this new version of the dataset. And then we inverse all of these transformations that we perform to get back to the original location. There's of course much more technical details in the paper, and I encourage you to take a look if you're interested. Just sort of a brief summary of some of the things that I didn't talk about here is that we look at on the theory side of things, we analyze the error on some sort of well-behaved distributions and give error guarantees depending on what kind of distributions we're working with. And then we perform a lot of experiments on both some synthetic data sets where we follow some of these distributions and then also on some real data sets and compare with previous works. And then we also analyze a more general error metric than this L2 error. And one of the key takeaways or key methods of our work is that the way we choose this scaling, where we prioritize either small or large values, that will depend on the error metric itself. So sort of the error we want to optimize towards is input to our algorithm, which is one of the a bit unique things with our work. And so the conclusion is that we outperform the previous state of the art when we have these distributions that show a lot of skew, and if they don't have a lot of skew, then we perform comparably to them. But that shows that it actually pays to take advantage of this skew for this problem. And that was all. Thanks for listening to the talk.
The timers we learned that issue from before. There's already a question here.
Yeah, very nice work. So could you maybe formulate this as like a more, I guess, general optimization problem where like maybe given a certain data set, you can like look at what is the best noise to add to like every dimension and maybe like scale things and do things like this. But I guess the key point being that like your solution depends on the given data set that you're given.
Yeah, and I think so. One of the things is that it also depends a little bit on the specific problem. One of our key techniques is this is adapting to the error metric that we're working with, and the error metric that is relevant to optimize will depend a lot on the actual problem, right? We don't there are also some other error metrics that we don't consider, and if those are the important ones, then sort of our techniques doesn't apply as much. So the idea is to sort of my philosophy is that we have to have several different kinds of techniques that we can use so that you can sort of choose a mechanism that works on your specific problem. And also some of our techniques, there are several different lines of work in this mean estimation. There's a lot going on with private mean estimation, and you sort of lie yourself on the scope from making no assumptions about data at all to assuming that data is from a very specific distribution. Typically, it's the Gaussian distributions because it has a lot of nice properties. We try to lie a little bit in the middle. We don't need as strong assumptions that it's a specific distribution, but we want to see, okay, what can we do if we have some assumptions on the data set?
Do we have more questions? Nothing. The next speaker can already set up while I'll ask a very quick one. No, you're not getting away already. So this is a pretty high-level question. Maybe I'm completely out there, but where does the data come from in the sense of does the adversary have any impact on introducing individual data points into the data?
Right. So here we abstract most of that away, but we assume that data is from some distribution whenever we analyze or error and things like this. But from a privacy perspective, we have to satisfy these privacy constraints, even if it's an adversary poisoning the data set. So there is sort of this disconnect between the privacy analysis. You have to take a very worst case approach. And then if we want to say anything about utility, we need some assumptions that the data look decent, at least.
Cool. Thank you. Thanks. Let's thank the speaker again. And next we have Alexander. He's going to talk about whatever's on the slide, microsec act. So take it away.
It took a few seconds last time.
Doing pretty well in this session in terms of issues with the slides.
Okay.
Well, now I jinxed it.
Yeah, I think there's a lot of animation. Okay, I downloaded PowerPoint as well, so I guess we can fall back to that.
Okay, great.
Okay.
Floor is yours.
All right, thanks. So yeah, this is microsec ag by Uegwo, Antigone Polychroniadou, Elaine Shi, David Bird, and Tucker Balch. So I'm not Uegwo. Yue was supposed to give the talk today, but because of visa issues, she couldn't be here. Okay, so I'm filling in. So first of all, what is secure aggregation? We have a bunch of parties. They have some private inputs. And the goal is for the server, which is the cloud in this picture, to learn the sum of all the user's secrets, but the server shouldn't learn any individual secrets. Okay, and so the threat model here is, of course, some of the users might be corrupted, and also the users can only talk to the server and they cannot talk to each other. Also, the users might drop offline and come back online later, and also the server itself might be compromised. The contributions of this paper are they improve the efficiency of existing secure aggregation protocols. Namely, they get 20 to 100 times faster than the previous best of BBG plus 20, and also 200 times less bandwidth cost, and reduced round complexity, while achieving the same level of security as the previous. Okay, and there are also a couple of follow-ups of this paper, Lerna and Flamingo. They both use the reusable setup idea of this paper that I'll present in a few slides. And yeah, Lerna is this quantum safe solution, and Flamingo is efficient for large models, which, yeah, this work could not handle. Okay, so in particular, there are two variants of the microsec-ag protocol that are presented in this paper. The first protocol is tailored towards small input domains, and some of the applications in this case are voting, number of page accesses and telemetry, testing results for contact tracing, and federated learning for quantized or sparse neural networks. And the second is more tailored to large input domains. And one application of this is also FL, but with the limitation that it only works for moderately sized models.
Okay, so first I'll present a sort of naive protocol based on threshold secret sharing. So here, each of the parties has their secret, and the first step will be sharing the secret to the other parties using some threshold secret sharing protocol. And it'll encrypt the shares to the corresponding other parties using some agreed upon key, send it to the server, who will then route these shares to the correct party. And then the parties will take these shares and add them up and send them to the server. And because we'll be using a linear secret sharing scheme, these added shares will correspond to a secret sharing of the added inputs of the users. Okay, and so then the server can take these and reconstruct the original model. Okay. So what's the problem with this solution? Oh, sorry, not yet, sorry. Okay, a benefit of this solution is even if parties drop out, because we're using threshold secret sharing, we can still reconstruct. Okay, so that's a benefit. But the main problem here is that this protocol has O of n communication per user per each iteration, which might be expensive. And so sort of the key insight of this work is, can we share something that is reusable so that you only pay this O of n communication per user once, and then in subsequent rounds, you don't have to pay this. Okay, so here's sort of the first attempt at using this sort of reusable technique. So here, there's some initial setup phase, and each party will have random values, R1 through R6 in this case, and they'll start by just sharing these values as before. Yeah, and that's it. That's the whole setup phase. And then in the aggregation phase, where each user gets their private secrets S1 through S6, what the parties will do is they'll just send to the server masked versions of their secrets using their randomness from the setup phase. Okay? And then following this, the server will see which parties actually sent these masked secrets in this first round and didn't drop off. And they'll send these identifiers to the users. And based on this, the users will send the sum of the secret shares of the other party's randomness from the setup, from which the server can reconstruct the sum of these masks and then subtract these from the sum of the original masked secrets from the first round to calculate the actual aggregated sum. Okay, so that looks nice, but there are some issues. So let's see how an issue might arise. So let's say there's a second round where the parties come with new secrets, it doesn't even have to be new secrets, but there's a second round, and the first user is offline for this round. So the parties continue the protocol as before. They send in their masked inputs using the same random value from the setup phase. And you can probably see where this is going. Yeah, they'll continue the protocol. And yeah, this time the server will reconstruct the sum random masks of all parties except for party 1, and from this compute the sum. But of course, using these two different sums, the sum amongst all of the users from the first iteration and the sum amongst all but the first user for the second iteration, the server can actually get R1, and so it can actually get the secret input of party 1 from the first iteration. Okay, so now let's fix this. And to fix this, yeah, we need to further hide these sums. And so now let me just quickly present the discrete log assumption. And here, if we have a large enough cyclic group G with a generator, then we know that for randomly chosen R, it's easy to exponentiate G by R, but it's hard to go back. However, if we have a small value S, then we know that not only is it easy to exponentiate by S, we can also easily actually take the discrete log if S is small. And yeah, so this sort of corresponds to the small input domain. For the larger input domain, this is where class groups come in handy. So class groups have an easy subgroup in which, yeah, doing a discrete log of even large values is easy. And then a separate large subgroup where discrete log is always hard, hard on large inputs. And so what they'll do in this eventual solution is they'll use the easy group to encrypt the secret inputs, but then add the mask in the hard group. And so, yeah, I'm not going to cover this too much, but this works for even larger inputs. Okay, so how does the protocol work now? So the parties will again compute the masked inputs using the same setup randomness in each round, but this time it'll send in G to the masked values. Okay, and then again, the parties will get the clients that participated in the first round, and then send in G to the summed random shares from the other parties. And from this, because we're also using a something like Shamir secret sharing, where reconstruction is actually just linear, the server can actually reconstruct in the exponent the sum of the randomness from the setup, and yeah, calculate in the exponent the sum of the secrets. And yeah, if the secrets are small, then it can take the discrete log. Okay, or if you're using class groups. Okay, yeah, and yeah, hopefully you can see that the previous attack doesn't work because even if you get G to the randomness of a party, this randomness will be large, and so yeah, you can take the discrete log. So yeah, I'll just wrap up quickly. They give some new secure aggregation for both small input domains and large input domains. Yeah, it cuts down the rounds of communication and also the overhead, and yeah, they have some additional improvements as well. But yeah, thank you.
Thank you for the talk. So I asked Alexander before if he can answer some questions, given that he's not an author of the paper, and he says he's willing to give it a try. So if you have any questions, go ahead, and if you don't get an answer, then you can just email the author.
Do I understand correctly that you reuse the same mask every round?
Yes.
Why? Because then you leak the difference between the private values every round.
I'm not sure what you mean, honestly.
Because if I, for some power consumption, you can see when it goes, if I participate in multiple consecutive rounds, then private value x1 plus mask, and the next round it's x2 plus mask. So you learn the difference between x1 and x2.
Oh, you mean like some side channel?
It's not a side channel. It's like you learn the derivative almost, like of the sequence of my values. You learn that I use more power consumption right now than an hour ago, for example, right?
Yeah.
No, sorry, I don't mean power consumption for the calculation. I mean, I'm imagining smart metering, for example. But sorry, that was a bit vague. But
I guess because it's summed across users, maybe you can't like identify what a particular user is consuming.
No, so I'll contact the author.
Sorry. Okay.
No issue.
Been already set up. And one quick question. Oh, there was one up there. Sorry, Ella.
I was wondering, maybe you could spend just a little more time on why the attack is now not possible anymore.
So basically the attack from the first attempt was that like the server gets sum of R1 through R6 in the first iteration, and then in the second iteration, it gets sum of R2 through R6. And so using these two, it can subtract and get R1. But here, all of that is happening in the exponent. So all that the server can get is g to the R1, but because R1 will be large, it can't take the discrete log, and so everything is still hidden.
But so the sum is also computed in the exponent, right? So couldn't you just like use the result, invert, multiply, and then you are in the small range again, and so you can just extract the result?
This maybe I'm not completely sure about, but
Email the authors.
Yeah.
I think is the solution here. Okay, thank our speaker again, especially taking questions on a talk that is not your own paper is really amazing and scary. So let's give him a big round of applause. Okay, next we have Sichan again. You're already familiar to us, and now he's going to talk about Swiss. Swissy, okay. Good, great.
Thank you for the introduction. Now I'm going to present to you Swissy. It's a joint work by myself, Kenny, Shika, and Bogdan. So last time I just talked to you about a more theoretical work on the security notion, and here we are going to have a construction, finally. So here, the name of the paper is quite complex. You get very complex words. So let's try to break down the title of the paper a bit. In fact, in this talk, I'm going to break down the title of the paper into three parts. The first part is what's SSE. You have already seen part of it in the first talk, but I will take a different spin this time. Then for the second part, I'm going to describe to you what's actually system-wide security. Why should we care about it? And finally, combining everything together, we are going to talk about the construction itself, the Swissy. So let's get started. So it's all boring slides again. It's going to be about what's searchable encryption. Here we have a client, have a server. I'm just going to speed through all of this. The client has a kind of a set of documents. It's going to construct an inverted index that it can search over. Then this inverted index is going to be encrypted and also to the server, which then we can perform queries of the type encryption of Alice. Then the server does some computation, returns the encryption of the document identifier. So far, so good. Except that last time I said that you can just simplify everything and consider the index retrieval problem, meaning that by the end of the protocol, the server returns the encryption of the indices of the documents that match the query. But actually, it's a quite big problem. And the problem is that no one actually considers how to actually retrieve the documents. This turns out to be a quite common practice, so to speak, in the literature. So if you look at one of the most famous papers, one of the most cited papers, it's like 3,000, 4,000 citations. It says in the search functionality, in the end, it's going to return the document identifiers. And if you look at newer papers, you see the same pattern, document identifiers. In this particular paper, Dori, of course, it returns the document identifiers, but inside the paper, there's a very interesting discussion about this document retrieval part. So for that, let me read essays. If after seeing the search results, a user decides to open and retrieve from the file system a file in the results, an attacker could infer that the file matches the query. Right, obviously it can, and that's a very big problem, which we call system-wide leakage. And this problem has been explored in a different paper called Rethinking SSE by myself, Kenny, and Shekhar. So here I'm going to give you a very high-level kind of conclusion we have from that paper. And the conclusion is as follows. So we consider two scenarios. One scenario is that we start with those index-only schemes, those that only retrieves the document identifiers. And then we couple that with a naive document retrieval system. Think about you just store the documents encrypted in an array without duplication, nothing. And then you just retrieve the documents based on the document identifiers you can fetch in the first step. Okay, if that's what we do, then the end-to-end system is going to be vulnerable to statistical inference attacks. Those attacks can recover either the queries or the data itself. So if that approach doesn't work, what else can we do? The second approach we can do is that, okay, let's not use a naive document retrieval system. Let's use something that's actually secure. Right? We can use ORM, we can use PIR, but in the end, if we actually do that, what we end up with is a system that's actually very, very expensive. We are talking about overheads that's in the range of 3 orders of magnitude or more. So that's not practical. So in this work, what we are trying to achieve is a scheme that's actually system-wide secure and it's efficient at the same time. We implemented Sweezy and we show that it's actually achieved those goals. It's really efficient and that's system-wide secure. And in this talk, I'm just going to give you a high-level idea on how do you achieve those properties. So before actually describing Sweezy, I want to describe to you what kind of leakage we try to hide in Sweezy. And for that, let's start with a naive document retrieval system. So here, the boxes you see on the screen actually represents encrypted documents. And the horizontal position of them represent the addresses they are stored in. Right, so if you see two things are aligned, that means the two documents are stored in the same position. They are the same document. So the first thing we are going to consider is that we are going to make a query, Alice. And in this case, it returns the first document and the third document. Then we make another query, Bob, and it returns the third document and the last document. And here what you can see is that the third document is accessed by the first query and the second query at the same time. And this information can be learned by the adversary, the server itself. And this is exactly the leakage that's abused by a lot of attacks. And this leakage itself is called co-occurrence leakage, if you are interested. So now let's see how Sweezy hides that leakage. Again, we are going to start with the same set of documents, and then we are going to make the same query, Alice, on those documents. We are going to do the same thing. We are going to retrieve the first and the third document. But the difference we are going to make is that after retrieving those documents, we are going to remove those documents from the server. Okay, then, and after that, we are going to store those documents in a local stash. This stash is maintained by the client, so it's not going to be seen by the server. Okay, if this is what happens, you can see how we can make a query on Bob without revealing this co-occurrence leakage. Right, what we are going to do is that we are going to retrieve the last document as usual, but the other document, the third document, is no longer stored on the server. The client can just search over the local stash to retrieve that document. So far, so good. Except that if that's the only thing we do, we are going to end up in a situation where all of the documents will be flushed to the client stash and there's nothing that's stored on the server. And that's a very bad idea because the whole point of searchable encryption is to outsource the storage to the server. So we are going to introduce one more procedure what we call the write back. And the process, as the name suggests, is going to write back a fraction of the documents that are stored on the client stash back to the server. And crucially, instead of just flushing them back to the original addresses, we're going to flush them back to new addresses. Those addresses can be computed by the client, but they are not predictable for the server. So that's the idea. And here, let's suppose that the documents, the two documents that were originally queried using Alice, have already been flushed back to the server. Those will be new addresses, of course. And then let's make a query on Bob again. And in this case, of course, we are again going to retrieve the last document, the last black document, and then we are going to retrieve the other document that's now sitting in a new address. And here you can see that the documents that's being retrieved in the two queries no longer overlap. And that's how we eliminate this co-occurrence leakage. Yeah, that's exactly what I have described. And on the last slide, what I'm going to show you is the performance of Sweezy compared to plaintext database. So here, what I'm going to see is just one of the parameters we have measured, and that's query response time. By that, I mean it's the time you start as soon as you make the query to the point that you generate the query tokens, make the query yourself, and retrieve the actual records. And the difference between Sweezy and the plaintext database is only about 1 to 2 orders of magnitude. And that's very impressive, consider that other solutions in the literature has much higher overhead. And with that, it comes to the end of my talk. If you're interested in the paper or the artifact itself, please scan the following QR codes. Thank you.
Thank you for the talk. Do we already have questions? Yes, up there.
Thanks. It was a very good talk. I wanted to ask, the solution seems to be restricted to one client, right? Because if you have, there's no extension to multiple clients.
Yeah, so for now, we only consider a single client because there's you cannot have 2 clients that stores the stash consistently. So for now, we only consider a single client solution.
Okay, thank you.
Okay, do we have other questions? We have time. Great.
Thank you for the presentation. I'm new to this topic, but I may ask a very stupid question. As see on this slide, the server removed the data point from the address. So will it be the case that the server know which data has been retrieved by their client?
What do you mean by which data? So in this case, all of the documents themselves are encrypted.
Oh.
Yeah, so they're only going to see the addresses. Since the address is only being accessed once and never used again, the server doesn't learn any information from that.
So the server will see everything as like random bits?
Yeah, exactly.
Okay, thank you.
Hey, cool. We have more questions. Great.
I'm also not working in this research area, so it might be a dumb question. So I wonder if you possibly consider that the server also learns the amount of query results from the client. Do you plan to hide that information as well in your future work?
So do you mean query response volume?
Like 3 records, maybe contains Alice's query.
So in this case, we only consider a single client and single server. So there's only one single client, and you cannot. There's no 2 clients to distinguish from.
No, I mean maybe the server returns 3 data points.
3 data points.
Yes. In that case, a server learns that.
Yeah, the server is going to learn the volume leakage. That's what we call the volume leakage. But in our case, we actually have a countermeasure against the volume leakage itself. It's a form of bucketization, and I invite you to read our paper.
Okay, thanks.
Thank you.
Thank you again for the talk. So. Yeah. Okay, great. Last but not least, we have Hayam talking about secure range searching using copy and recurse. The floor is yours.
Thank you for the introduction, Stephanie. So I was told that you are more likely to remember the last talk of a conference. So I hope to leave you with good memories of PETS 2024. Yeah, so this is a work together with Eyal Kushnir and Guy Moskovich. We are from IBM Research. The motivation for our work is databases that are encrypted with FHE, fully homomorphic encryption, usually stored on the cloud, and that we want to query with queries such as what is the average sugar level of patients whose age is between 30 and 40, and LDL level is between 130 and 160. So it should be mentioned that we are interested in non-interactive protocols, so that's only one round. So solutions such as ORAM and other MPC techniques are not applicable. So we have to go with FHE, fully homomorphic encryption. And it is also worth mentioning that there are already companies that provide analytics as a service with FHE on the cloud. So it makes sense to try to improve these services. So we think of our database, or the records in our database, as points in some higher dimensional space. In this case, it's going to be a two-dimensional space where the x-axis is the age and the y-axis is the LDL level. And the query that we see here is actually a rectangular region, and we want to query something on the points inside this region. So our solution is not restricted to rectangles. It can also be more general ranges and higher dimensions. But in this talk, for simplicity, I'm going to assume the database is only one-dimensional. That means points are actually one value. And the ranges are going to be a segment, all the points between A and B. And the goal for this talk is going to be just to count how many points are inside the ranges, inside the range, the query range. See the paper for details for higher dimensions and more generic ranges and more complicated functions. This talk is going to be simple, I hope. So what would the plain text algorithm do? Let's start with something simple. So assume you have a database with P being 1, 2, 4, 4, 5, 7, 7, 8, 8. The plain text algorithm will partition these points into groups and try to make something of each group by itself. So a partitioning could be like 1, 2, 4, 4, 5, 7, 7, 8, 8. And we can also store with each group a bounding segment that is the smallest point and the biggest point. So I'm going to use interchangeably the point with value because higher dimensions is point, but for one dimension, a point is a value. So each group is going to keep a bounding segment, which is the smallest point and the biggest point of each group. And if we have a query range such as all the points between 5 and 8, then we can quickly see with little checking that the bounding segment is disjoint from the query range. And so we can know that we can skip all the points in this group. We can just ignore it. Similarly, we can see that the bounding segment of the third group, 7, 8, is totally contained inside the query range. So we can just count all the points inside this group without any further checks. The middle group is more complicated. So this, the bounding segment crosses the query range. So we cannot say anything intelligent about the points inside this group. And we have to look into further partitioning of this group and continuing recursing with this group. So this suggests a tree-like data structure, which is called in the literature partition tree. So in this example, this is a ternary tree. Every node has 3 children, but 3 is just a parameter, R, but it can be of a different value. So the leaves of the tree are going to be associated with elements of the database, and inner nodes of the tree are going to be associated with subsets of the database, which are the values in the leaves of the subtrees that they have. And also each node is going to keep the bounding simplex that bounds the points inside that it represents. And for one dimension, we can also say that at each node, the query range is going to cross at most 2 children, the bounding segment of 2 children, which is also a guarantee that we will need to recurse in plain text. We are going to need to recurse into at most 2 children. So generalizing this to higher dimensions is very complicated, details in the paper. So what are the challenges of FHE, fully homomorphic encryption? So with FHE, we cannot skip a group. We cannot ignore a group because FHE works in circuit model. We need to apply the same set of operations for every input. So we cannot just ignore a subset. And as was already noted earlier in this conference, in one of the earlier days, we need to do something with every node of the tree, but this thing can be very simple, like a multiplication or maybe 2 multiplication. And we should strive to try to minimize the number of comparisons that we make. And actually, comparison is what takes most of the time for the algorithm, both the plain text and under FHE. So it makes sense to try to try to minimize the number of comparisons. So let's denote by T the time to make a comparison between a query range and a bounding segment or a point. And we want to express the time complexity with T also, and not only with N. So the plain text algorithm would take T times log N. There's a lower bound for FHE of order of N. The naive algorithm under FHE will just check every point whether it is contained inside the range or not. So that would take O of T times N. And our algorithm will take order of T times log N plus N, which seems to be the best we can hope for. We are going to do that with a technique called copy and recurse, which is what I'm going to describe next. So if there is one thing that we're going to take from this talk, I mean, I hope you're going to remember everything from this talk, but if you're going to take one thing from this talk, let it be copy and recurse. So what is copy and recurse? So copy and recurse is a technique to efficiently traverse a tree under FHE. So we are focused on FHE, but this is like more general and can be applied to other MPC techniques. So using copy and recurse, traversing a tree takes the similar time complexity to the plain text algorithm, but we are going to pay a linear overhead. So copy and recurse needs 2 prerequisites. The tree needs to be full, and we also need to have an upper bound of the number of children that we need to recurse into at each node. So let's see how copy and recurse work. So we started the root. The root in this case has 3 children. We compute for each child whether we need to recurse into or not. So this is done under FHE. So under FHE, we're not going to get a result, a plain text result that we can make a decision on, but we're going to get a ciphertext that is going to encode a 0 if we don't need to recurse into that child, or 1 if we do. And remember that we have a bound, that there are at most 2 children that we need to recurse into. So this example, by the way, does not comply with the previous example. So here we're going to recurse into the middle child and the right child. So after having figured which children we need to recurse into, we're going to use a selection matrix. So a selection matrix, you think of it as a generalization of a MUX, a multiplexer. So a multiplexer gets 2 inputs, and using a condition bit, it selects which of the inputs is copied to the output. Selection matrix is a generalization of that. It gets R inputs, and using the indicator vector, it copies some of those R children to the output. So after having copied the children that we need to recurse into, we recurse into them. And the nice thing about it is multiplying by the selection matrix yields linear overhead, but after we have done so, continuing in recursion into the children takes the same time as the plain text algorithm. So the time bounds for our solution, well, I'm not going to read it. You can read it by yourself later or now or sometime later. We implemented our algorithm, and the experiments show match what we expected in theory. So you can see here the blue line is the naive algorithm. The other lines is our algorithm with different parameters of R. So you can see that everything in asymptotically, everything is linear, but our slope is smaller than the naive slope. We also pay some overhead that is more significant when n is small. We also implemented it in 2 dimensions when the ranges are axis parallel rectangles. Again, things are more or less linear, and there's some overhead that we need to pay. Again, this is what we expect from the theory. So now to recap, so we showed copy and recurse, which is a technique. We focused on FHE, but it's not only for FHE, for any arithmetic circuit, actually. Copy and recurse, a technique to traverse a tree efficiently. With it, we showed how to traverse partition trees, and we used partition trees to show how to answer range queries, range searching queries. So I think I have 30 more seconds. So I prepared a haiku version of this talk that you can enjoy on your way back on the train, unless you live here, and then you don't. You'll have to enjoy it somewhere else.
Thank you for the talk. Questions up there?
Thanks. Really interesting talk. I have a couple of questions. So how do you decide if you recurse or not? You mentioned this is done under FHA. Is it like some kind of comparison?
Yes. So you need to implement comparison under FHE. So this is okay. So let's stick with the one-dimensional case. So this has to do a lot with the scheme that you're using. So if it's CKKS or not. So let's we implemented it under CKKS. So under CKKS, so basically you have two segments, like the query segment and the bounding segment. So you actually need to find whether one endpoint is between the other 2 endpoints. So that's 2 comparisons. So basically comparison with CKKS is done by taking, by checking the sign of the difference. So for the sign function, there are a lot of work of how to compute the sign function. So just take 2 differences and see if the signs are different. If they are different, then well, you're in this position, this position. Yeah, so I hope that answered the question.
Yeah, it does. Are you taking advantage of batching in any way?
Of what?
Of batching, like packing
Oh,
capabilities?
yes. So our technique is indifferent to packing. So it works with TFHE, for example, with no packing in TFHE. With packing, so well, obviously the easiest way is to just perform the query over 60,000 databases in parallel.
The reason I'm asking, sorry to interrupt, is that in one slot of the packed message, you might need to recurse, and in the other, you might not need to recurse. So I wasn't sure like how this actually gets resolved. And if you're not using packing, like why not TFHC? Wouldn't it be more efficient?
So our solution is indifferent to the scheme. So yeah, it can work with TFHE as well. We were more interested in CKKS because, well, it was our motivation came from CKKS actually. So that's why we were interested in CKKS, and we actually used to search many databases in parallel. So we took the easy way out.
Makes sense. Thanks. Very interesting work.
Thank you.
Someone else was first. So maybe you did this in the paper, but is there some analysis as to what is the optimal choice of R? And one reason why I'm also asking is for another paper that was like also tree related, the optimal value for R in that case turned out to be E. So I'm wondering, like maybe there is some version of the algorithm where if you sometimes switch between, let's say, 2 and 3 or 3 and 4, that you might get a better result than just
Yeah, so that's an excellent question, by the way. Yeah, so you can see that for different choices of R, you do get different times. Yeah, so we didn't actually think of how to choose R more intelligently than just checking all the R's.
Thank you. But it's a very exciting algorithm. Thanks.
Thank you.
So I suppose the sign function you were talking about is like if A is less than B, then sign is 0. If they are equal, it's half. And if A is greater than B, it's 1, right?
Yeah.
Okay. So how do you approximate that function? You mentioned like you are using CKKS, and hence I guess.
Oh, so there are a lot of work in that area. So we didn't. I mean, we just used what was best of practice. So yeah, I think it's better to take it offline. Like I can give you an intuition, but the details you have to read the paper.
Thank you very much.
Let's thank the speaker again. So this was the last talk of our session and also of the conference. You still have the closing ceremony, the closing remarks back in the main lecture hall, but let's take the time to also thank our technical teams and our volunteers.